So it's a great pleasure to introduce Dr. Oliver Jennrich. Oliver studied physics and obtained a PhD in Hanover and completed postdoc positions at Gila, Colorado, and at the University of Glasgow. Since 2002, Oliver has been at the European Space Agency working on gravitational waves as a scientist in the LISA Pathfinder mission and the LISA study. He has side interests in X-ray missions. He's the European project scientist for the Japanese SUSSP mission. Am I saying that right?
Yeah.
SUSSP mission. And high-energy particle physics, the USO experiment on the ISS. Okay. Oliver.
Okay, thank you, Christian. Thank you for... So thank you for inviting me to come here and entertain you this afternoon. So this will be a series of 3 lectures, or rather talks. So each talk should be around 45 minutes. We obviously have a little bit more time than that, so I won't rush through it too quickly. And please, if you have questions, ask at any time. The first presentation I'll give you now will be about sort of the science of low-frequency gravitational waves. The second one, before the coffee break, will be focused on the LISA mission. And then after the coffee break, I'll give you a little bit of insight into the LISA Pathfinder mission. And I have to tell you that all of what I'm telling you today is sort of the top of the iceberg, right? So 3 hours are not enough to get into the details. Even 3 hours are not enough. So if you have any questions, please ask. If it gets too detailed, I might defer you to later discussions or to email or whatever. But please, this is a school and not just a colloquium talk. So please feel free to ask questions whenever they come up. So one of the questions that I get quite recently, certainly after the LIGO ground-based detections, is why do we even bother with space-based detectors? And this is a little bit a question to me always sounds a bit like, a little bit born out of ignorance of what gravitational waves can actually do. Because in my view, this is simply like asking if we have this is the VLT in Paranal in Chile, or that one, which is the VLBI, a part of the VLBI, or even that one, which many of you might not recognize, but this is the LOFAR, or a large part of the LOFAR radio telescope, which are effectively very, very simple receivers in the Dutch countryside and a couple of other places in the world with extremely sophisticated data analysis behind that. If you have all those, why do we need things like the JWST or the Hubble or other things that are in orbit? And the answer is that different detectors have different purposes. So different detectors aim at different signals, and different detectors might actually be sensitive to different kind of gravitational waves in different frequency range. So this is something you will see later. Again, this is the sensitivity curve of a typical space-borne detector like LISA. And I just want to point out, unfortunately the resolution is a little bit low here, so I probably have to read out most of the axis to you. But those of you sitting in the front row will see that the best sensitivity or the lowest noise is around a few millihertz. Now if you compare that to ground-based detectors where that minimum is somewhere between, let's be optimistic, a few hertz to a few hundred hertz, you see we are, 4 to 5 orders of magnitude below that with gravitational waves in space. And space-borne detectors typically are low-frequency detectors. You wouldn't go into space if you hadn't the need to go for low frequencies. And why is that? Well, here you see I try to plot on the same scale the sensitivity of a space-borne detector with the sensitivity of LIGO as it is now and the sort of final design sensitivity. And you see it's in a different frequency range. Ground-based detectors are way more sensitive as well. So with spaceborne detectors, you're typically looking at low frequencies and low sensitivities. And the reason for that is kind of obvious. You don't want to have the whole complexity that you have on ground-based detectors. So the saving grace there is that low-frequency sources are generally very, very loud. And if you want to have sort of a hand-waving argument why that is the case, is the emitted energy is a fixed proportion of the masses of the constituents. I mean, you probably have heard ad nauseum in this school that they emit about a few percent of their rest mass into gravitational waves, and that's kind of a lot if you're talking about things that are at masses of 10 to the 5 to 10 to the 7 solar masses. The frequency goes like 1 over m. The heavier the system is, the lower the frequency. So that means that the emitted energy roughly goes like 1 over f. So you can afford lower sensitivity in space-based detectors simply because your sources are typically way louder than those on the ground, than those you can detect on the ground. And there's something which probably you heard discussed earlier in the ground-based lectures on the ground-based detectors as well, something which is sometimes called the seismic wall. And I sketched that here as, thanks to PowerPoint, somewhere around a hertz or so. And if you think about that, the seismic gradient forces or gravity gradient forces, they are unavoidable. You can't shield gravity, right? So you see the effect of whatever moves at low time scales. So that could be people like you walking around next to the detector. Okay, you can shield that by building a big fence and keep people out, right? You can do something about ocean waves hitting the shore, which is about 0.7 hertz or something like that. Those of you who have been at the beach this morning might have seen that, although there was pretty little surf this morning. But this is about the time scale of 1.5 seconds or so. Now, if you go to time scales of 1,000 seconds, or 10,000 seconds, or even 100,000 seconds, 100,000 seconds is about a day, right? And if you want to catch 3 or 4 cycles, you're talking about 3 or 4 days. Now, if you think about systems or noise sources that occurs at frequencies of 10 to the minus 5 hertz, so timescales of days, it's the weather, right? This is a typical lifetime of a low pressure system. Now, if you want to enjoy yourself, just calculate the mass difference between a high pressure system and a low pressure system in the atmosphere. That's a truly humongous mass moving around. All of that pulling at your mirrors, right? So, and good luck with shielding that one. Or building a fence or building a huge dome. It simply doesn't work. So the other problem that you have, of course, is that things underground move as well. It's typically something we don't recognize very much unless it's violent in earthquakes, but magma flow happens on timescales of days or more than days as well. So you have density fluctuations all around you, and they're really not very well controllable or measurable or diagnosable, so that with some fancy data analysis techniques you can identify those and take them out of your data stream and say whatever is left must be a gravitational wave. Plus, it's not terribly convincing. So if you want to go to low frequencies, you pretty much have to go into space. How we do that exactly is topic of the second lecture. In this one, I want to convince you that's actually worthwhile of doing that. Because it's all nice and shiny to say I can build a fantastic instrument at 10 to the minus 5 hertz and I can see things with enormous signal to noise ratios, unless you give your funding agency a good reason, better more than one, why this is actually cool science, you're probably not getting the mission. So this is sort of a pictorial description of the 8 big areas of science that we identified for a space-based gravitational wave detector. In other words, LISA, so from the top and then clockwise, neutron star binaries, supermassive black holes, what we call extreme mass ratio spirals, the progenitors of LIGO sources, testing general relativity, looking into cosmology, and looking into things that might happen even before the cosmic microwave background, and then the things we don't know that happen, but we are pretty sure that we will see something. And let me just give you a little bit of insight why these things are cool science. So, when you think of compact binary stars, we are typically thinking of white dwarf binaries, or neutron star binaries, maybe even black hole binaries of stellar mass, so 2 or 3 stellar masses. And in various combinations, you can have black hole, neutron star, and all that. The important thing is that they are compact, which means that they survive the in-spiral and the tidal forces long enough so that gravitational waves take over in terms of losing energy in the orbit. If you think of two normal stars, gravitational waves don't play a role there because they have mass transfer once they get into the common envelope, and things spiral down and sort of mix very, very quickly just because of friction. So that's boring. That's interesting as well, but it's boring for gravitational waves. So we need to concentrate on the compact guys who are hard to disrupt. So out of those, the white dwarf binaries are by far the most numerous. The other ones are a bit exotic. And the reason why white dwarf binaries are interesting is these are one of the potential progenitors for supernova 1A class explosions. And you know that these have been used because of the way or the ease with which you can calibrate them in terms of luminosity and distance as part of the cosmic distance ladder, and play a huge role in the determination of the expansion of the universe. And cataclysmic variables play a role there as well. So we don't actually know that much about those white dwarf binaries, apart from the fact that if you take galaxy models and calculate how much there should be out there, provided that you understand how the galaxy works, it should be millions. Now, the problem there is provided that you understand how the galaxy works, because you might not, and then all your predictions are wrong. So one of the ideas there is, can we access those white dwarf binary systems more directly? The problem with them is that they're a little bit hard to detect electromagnetically. I don't have the exact numbers. I tried to find out before I gave this talk, and the numbers are a little bit confusing, but it's a few tens, maybe hundreds, but not much more than that, of white dwarf binaries are known today. And the problem is they are not very luminous. And the problem even worse is that you typically don't have the resolution to see that this is a binary. Even Gaia might have difficulties there. So you have to rely on eclipsing binaries. So that these are those that you see edge on, and then one passes in front of the other, and the brightness curve changes. And Gaia is supposed to get up to 150 or so eclipsing binaries. Now, the Gaia project scientist sits just a couple of offices down the corridor, and I asked him when we can expect the first census of eclipsing binaries in the galaxy. That will take some while because it's foreseen for the third data release, which will come a little bit down the line, maybe in 5 or 6 years or something like that. The Large Synoptic Sky Telescope might see on the order of 1,000 eclipsing binaries, which is not bad. So in case you wonder what is an eclipsing binary, I have a nice luminosity trace here, and you see whenever the two get in front of each other, or halfway in front of each other, then the luminosity or the flux here drops a bit. And LISA will see about 25,000 or so. And that's not because LISA is such a fantastic instrument in spotting eclipsing binaries. No, it's just because you don't need eclipses. Because these things emit gravitational waves no matter what. It doesn't matter if they're edge on or phase on or anything in between. You just get a different polarization of gravitational waves. So you have immediately a much larger sample. And there's a very small number of binaries that both LISA and the optical telescopes like Gaia or LSST will see. So it's in the small tens, so there is a little bit of an overlap there. And if you have the numbers, and ideally the spatial distribution, are they mostly in the disk? How many are in the halo? Is the sort of luminous star disk the same as the white dwarf disk, or is the distribution different, and all that can help you to anchor the models for our galaxy evolution. So that will effectively, that's a fancy way of saying, it will tell you if you understood the galaxy right, the evolution of the galaxy, or if you simply extrapolate to some bullshit from the few numbers that you have. So the signals that we get from those are kind of boring because they are simple sinusoidals with an almost fixed frequency. It's not precisely fixed. There's a small drift because the frequency increases because, of course, they lose energy through gravitational waves. Otherwise, we wouldn't see them. But this is so little that we can only see them in our galaxy, and it won't affect the orbit and hence the frequency too much. So the total number of the galactic binaries in the LISA band is extremely large. So there's millions upon millions. And we will suffer from something that the astronomers call a confusion. They usually use that when they have too many sources in one diffraction pattern. So if they look at extremely dense star clusters, it can happen that the diffraction pattern of a telescope covers 5, 10, 12 sources, and then you can't really tell if it's one source or 5 sources with twice the intensity. And we have simply a problem like that as well, only that it's not about spatial resolution, but there are so many that we will have plenty per frequency bin. So we can't really, if we put in this boring sinusoidal signal over 4 years, there will be maybe 10 at that given frequency, of which the frequency only differs by, let's say, 1 over 10 years or something like that. So it's very difficult and impossible to distinguish between them. And therefore we call most of them a foreground noise. So this is something rather embarrassing in a way. You create an instrument that's so sensitive that it's blinded by your galactic foreground. However, there you go. Even a noise can deliver signs, which is a familiar topic in gravitational wave detection, because the detector is not aligned with the plane of the galaxy. So during the lifetime of the detector, it will see the galaxy disk under different aspects, and therefore the noise will be modulated. And the depth and the frequency and the details of this modulation will tell you a little bit about the spatial distribution. That's something that probably no other detector can do at the moment, certainly not electromagnetically.
Excuse me?
Yes?
If there was like other LISAs flying around,
yeah,
and we had better sky localization, would this be of less? Because I feel like electromagnetic waves have a lot of background / foreground.
You might have. So the answer is yes. You can improve things by putting more detectors in orbit, right? Because that allows you to pinpoint your sources better and sort of try to subtract them out of the data stream. Another thing that helps is you might want to run your mission longer, which allows you to distinguish more finely between neighboring frequencies. And you might have heard of a mission proposal that was called the Big Bang Observer, BBO, that had exactly that idea with effectively 4 LISA detectors. And to take out all the binary signals from the data stream, to dig down to what's left then should be something like gravitational background radiation. But for that you need to subtract almost all of those Newton star binaries, which is, even with 4 detectors, a rather challenging problem. So yes, you can make it better if you have more detectors. I think that's always the case, right? But you really need to work hard on that one, because there's one thing that will come up later again. If you do this quick mental calculation, what is your resolving power of your instrument? I haven't told you that yet what the orbit is, but most of you will know anyway. It's in the Earth orbit, so around the Sun. So if you look at a half-year time scale, you can imagine that you build a telescope or detector that with synthetic aperture of 2 AU, right? If your sources are long-lived enough and you can track them. And now that sounds cool compared to normal electromagnetic telescopes where we are 30 meters, or with VLBI with, let's say, a class of 10,000 kilometers. The problem is we had millihertz, and a millihertz turns out to have a wavelength of about 2 AU. So you're in a situation where your detector effectively is completely dominated by diffraction. So the wavelength of your signals are about the same size as your detector, which already tells you that you shouldn't expect wonders in sky resolution. Right. I mean, this is the disadvantage of low frequency. Everything is big and takes forever.
Another question?
Yeah.
What makes binary what you're resolvable by Lisa and what not?
Distance. So the galaxy is, I don't know, 20 kiloparsec or something like that. We have identified, I don't know, will that slide come soon? It probably will come, I can tell you anyway. We already know a couple of white dwarf systems optically or through radio. They are relatively close, maybe a kiloparsec, and which means that they're louder, right? That's like you're sitting in Wembley or wherever your preferred football stadium is, and with it sold out and everybody is cheering, you can still talk to the ref because he's close, despite the fact that he's not louder at all than all the others. So that's a bit the situation. As long as they are close, you can see them. And the density, obviously, they are fewer very close than far away for very obvious reasons. So we think that we can get maybe 100, 200 or so of what we call verification binaries, because we know that they are there, we know that the frequency, we know the sky location. So this is one big advantage. You don't, with a detector like that, you don't have to hunt for signals, they're always there. The problem is you don't have to hunt for signals, they're always there, but we'll come to that later. So there we are, like I said, it's about 25,000. About 5,000 we might be able to follow up with electromagnetic, or at least have enough signal to noise to do precision measurement on the orbital period and the mass and the distance. So maybe a few tens joint sources with LSST and with even fewer with Gaia. So, and this is what I just said. There's the slide with the little graph. I apologize again for the resolution. I should have made them bigger. Anyway, so some of them we call verification sources because we pretty much know everything about them, what's supposed to be known. And when I say, well, we see a couple of thousands, that typically means integration times over a couple of years, the lifetime of the mission. Those are loud enough that they peak out of the noise at a few weeks of integration time or data accumulation. And they're not really needed, right? Because in terms of making sure that the detector works. But it's very nice to have a guaranteed detection, that you don't have to wait for something. You know that you can establish the sensitivity of the detector independently, but it's very nice to know that you don't have a rate problem where you have to wait for the signal and people start tapping their feet. Where's your first detection? I mean, this thing will come up very, very quickly and will get people off our back. very, very quickly as well. So, enough on compact binaries, because they are so incredibly local. Let's go to something which is a bit further out there. And these are sort of, I would say, the 500-pound gorilla in our science case, which means that whenever you think about requirements for your mission, those absolutely have to be in there, because might be the only ones who have a chance to see them. So massive black holes we call black holes with a mass of larger than 10 to the 5 or so solar masses. And it really doesn't matter if this is constituent or final, they're all big. So as you know, we think most galaxies have a black hole in the center. Our own galaxy has a black hole of about 4 million solar masses in the center. So, and we are a pretty box standard spiral galaxy, so there's no need to assume that we are different from others. So most of the spiral galaxies will have something like that in the center. And the question is, how do they get there? And so if you go far back in time, very, very far back in time, so when the first stars formed and the first galaxies might start to assemble, then the question is, how did these monsters in the middle sort of get into being? Because they certainly didn't appear with 10 to the 6 solar masses. Or maybe they did, but then we wouldn't know how. But the question is, the current theory or the current idea is that they started out of something smaller, maybe 100, maybe 1,000 solar masses in the center, and then they grow, right? They accrete cold gas, lots of cold gas, and this is sort of their main feeding channel. And every now and then they will swallow something else. And they will swallow white dwarfs, maybe, or neutron stars, if they existed at that time. Other black holes, maybe from other smaller proto-galaxies. And then the question really is, what happens? Is that a system where sort of a small one eats other small ones, so that all the collisions are between black holes of the same size? Or is there a hierarchy of black holes in the very beginning that maybe the whole interval between 10 solar masses and 1,000 solar masses was populated, and now the bigger ones eat the smaller ones? And then there's as well the question of the gas accretion and the accretion of black holes. How does that work? Is this completely chaotic? So if this black hole is the bigger one that survives, is sitting there, is the gas and the rest of the matter coming from all different directions? If so, you would expect that the final spin of that system is sort of around 0, right? Or is it a preferred direction? Does it come from a disk maybe already? And then you might expect the black hole to spin up. And then you would see, instead of having mergers between sort of randomly oriented small spin black holes, so maybe a few percent spin or something like that, if you have chaotic accretion, or if you have directed accretion where everything comes from a disk, then you might have still randomly oriented black holes merging, but both of them maybe with a spin of 0.9 or something like that, which gives you a dramatically different signal. And there's an interesting cartoon in that one that I borrowed from somebody. Oh, the name will come back. These are all these mergers here, sort of, and occasionally you see somewhere here, you see two black holes surviving there that then will merge and give you a signal that looks roughly like that, right? So this is our poster child general picture of a black hole merging. Now this has been numerically calculated, among others, with the help of Joan, who's sitting in the background. We'll tell you later much more about that, I suspect. But of course now everybody knows how the thing really looks like, and it looks remarkably similar. But just to emphasize that again, all signals of black hole mergers look like that. Right? You can draw that one, and the only thing you have to do is you have to change the time base here. Heavier systems take longer, and I think if I guesstimate here, it's about it says it's a 10 to the 6 solar mass black hole binary, something like that, because it has 1,000 seconds, and in this game the sun is the radius of the sun is 5 microseconds, or something like that. So there you are. And this is sort of the idea of how the signal looks like. But anyway, this is how the signal, and each of them will give a signal like that, just in different frequency. If it's smaller, the constituents are smaller, or in a lower frequency, and with a little bit more amplitude if the things are lower. And with that, you can actually distinguish reasonably well between scenarios where you say, well, probably most of the accretion is chaotic, or you can say probably most of the accretion is coherent. So there have been disks in the early universe, and then the obvious question is, where are they coming from, and why are they there? And but these are all things at redshift of 10, 15, something like that. So in areas where typical electromagnetic systems are not yet capable of seeing things.
Excuse me.
Yes?
Could I ask, what's the time scale on the vertical axis?
The time scale on the vertical axis is not really a time scale. I took out deliberately the unit here because at that point it's meaningless. Consider that arbitrary units, because peak effectively gives you the mass range of the things. But typical strain here is 10 to the minus 20. So you would see about the usual picometers on millions of kilometers distance, or attometers on LIGO scale instruments. It's roughly always the same. It changes, of course, with the mass, but it's linearly with the mass, but it's not terribly different from system to system. So those things have very large signals, and this is what I told you at the beginning. Because they are low frequency, and the emitted energy is proportional to the mass, and the frequency is inversely proportional to the mass, you should expect an enormous amount of energy coming out. And so you see, they have extremely large signals, and with a decent sensitivity space-based detector, you can see them to the edge of the universe. So wherever they happen, well, of course, at some point, if you insist to go redshift of 100 or so, you can't see them anymore. But let's see to everywhere where astronomers nowadays believe that we actually do have galaxies forming, right? We will be able to see them. There might be a surprise there, maybe things from very much earlier than we think they do, but we will see that when it happens. A side effect of the large signal is that we have reasonably good parameter estimation. I told you there about galactic binaries, that there the signal to noise is maybe 10, 20 or something like that, so not terribly high. Here we can get signal to noise is plotted here. The brown area there with the 10 to the 6, 10 to the 7 solar masses out to a redshift of 3 is signal to noise of 3,000. So you won't be able to see the noise, in other words, right? If you take your pen and draw out the line, the noise is still smaller than the thickness of the line you're drawing. So this is sort of it looks like a numerical signal. And here, so around 100, 200 or so at redshifts of enormous, you can start seeing the noise creeping in. And that allows us to determine the mass and the spin parameters to a few percent. And that in turn allows you to tell you, well, most of the things we see come in with 10% spin or something like that, then probably everything is chaotic. Or it says, most of the mergers we see are with black holes that have almost maximum spin, so 0.9, 0.95 or something like that. So they have been spun up by accretion, so that means that there's a preferred angular momentum, which typically means a disk. The cool thing about that is that you see these things at places where optical telescopes have a hard time looking at, because they're sitting, if they emerge, in the center of galaxies, where it's typically dusty, and which is not a good place to be if you want to see that through even an infrared telescope. Now, another thing that happens at the center of galaxies is something much less spectacular than these things, where enormous energies come out and all that. And you know, when you talk to, if I give these public talks to where children are present, they always, you know, black holes are cool and colliding black holes are even cooler. But there are other things that are much less spectacular, but at least as important. So, and these are our extreme mass ratio in spirals. Now, what is an extreme mass ratio in spiral? This is typically where we say when the mass ratio is about 1,000 or so. So think about a stellar-sized black hole mass, black hole falling into the center of the galaxy, something like that. And then these things, and this is a plot here that I borrowed from a publication from the Gillison group. It's rather old now, from 2009. These plots the orbits around our Milky Way's black hole, and you see them going all the way around. And the only reason I put that up there is because, in addition, on top of those, there might be a handful of black holes that you can't see, right? And when they go around an enormous amount of time before they eventually coalesce with the body in the center. And you know the perihel advancing of the Mercury, sort of the poster child probe of the general relativity in our solar system. You know, these things do the same, but because you're not in this gravitational field of the sun, but a gravitational field of something that's a million solar masses, the effect is much stronger. So the orbit will go around like that, and eventually mapping out all the potential around the central black hole. And this has two effects. The first thing is that the signals are extremely complex and depend really critical on mass and spins, and it's, you change a little bit and the signal looks completely different. It looks roughly like that or like that, depending on the time scale, on the masses and the spins, and you see this is very much different here. You observe many, many thousands of orbits, so you have a high precision probe of general relativity. You use general relativity to calculate those signals. You might have heard that this is one of the outstanding challenges, which is really not very well done at the moment, because it's very, very complicated to calculate these things with extremely high precision. But if you can do that, or if you can devise a way to sort of guess your way around through the waveform so that you get an idea what's going on, you can have an extremely precise test of general relativity, because if general relativity is wrong and it's not a Kerr metric, for example, the thing would look likely different. And if you observe 1,000 orbits, things run out of phase very quickly. The problem is the signals are not spectacularly large, and they're difficult to detect. So we think that we might see them out to a redshift of z equals 4 or something like that. That might be a bit optimistic, maybe a bit less than that. The challenge here really is that the signal templates are computationally extremely expensive. So those of you who do numerical relativity, there's a challenge, as I'm sure people have told you already. And then there's something which we didn't know when the last proposal was written, but we did know when this current proposal was written. And this is the new kid on the block, Astrophysics of Stellar Black Holes. And here I plot again the two sensitivity curves for LIGO and for space-based detectors. And this here is about GW 150914, so the first detection. And it didn't take long after the detection of people realizing, hang on a moment, if this is 30 plus 30 solar masses or something like that, they didn't live that long before they arrived here. So a few months back, they might have been at a tenth of a hertz. over here. And with an amplitude that goes up like that, so there would have been bang in the band of a space-based detector. Now, we always had source classes that we jointly addressed with the ground-based community, but so in a way, millions of years before they ever became ground-based observable, it's our neutron star binaries, or black dwarf, white dwarf binaries, because they take another 1 million or 2 million of years before they finally coalesce into something like GW150914. And in this time, of course, you can't build a detector that lasts 1 million of years. So you can just do sort of population studies and say, well, I have that many, so I expect that many over there. This year is completely different. I always compare that to in the old system, before we knew about that kind of sources, that you look at the population out on the street and you see people pushing prams with babies in there, and you see very old people, and you see middle-aged people, and you conclude that, or probably there's a process that converts that little thing in the pram to that guy over there with a walking frame, right? Now here, with this system, you take them by the hand and walk through their life, at least through the end of their life there, right? You can observe the aging over a few months. Well, you can't really observe them because there is this gap where we don't have a detector, but at least you can identify this system and tell the ground-based community this system will coalesce in 5 months, 3 days, 2 hours, 12 seconds, and 512 milliseconds. So, which is a great thing to do, because it probably allows you a bit better to narrow down the formation channels of these things. So let's come to the next thing, which might sound a bit exotic, but don't be worried, it gets more exotic. The fundamental nature of gravity. So there are a couple of axioms in general relativity and a couple of very simple outcomes. And one of the very simple outcomes is that a black hole is determined by 2 parameters, mass and angular momentum, spin. Right? Well, technically charge as well, but considering that we have absolutely no clue how a charge should be maintained in an astrophysical black hole, let's ignore the charge for the moment. So, and that's effectively saying that no other parameters determine that black hole. None of its history, if it came together through mergers or through something else, everything has to come down to mass and spin. It's called the no hair theory, which means, it's just a shiny little ball with no hair sticking out. And however, if you look at the black hole mergers in the numerical simulation, you will realize, if you have seen them, there are 2 spherical thingies coming together, and they form a kind of a peanut for a brief moment, and then it wobbles a bit, and then it's a sphere again. Now, during the wobbling, the shape of that thing is radiated away in gravitational waves. And you can calculate how that should look like. This is the called ring down signal. And in the simulated signal, you see it over here. Unfortunately, in the LIGO signals, we can't really see it at the moment. So the frequencies that show up and the Q factors are dependent on how many modes are emitted. And that's a very nice probe on the final state of the black hole. Is actually everything radiated away the way we expect it to be, or is there something in addition? So it's a good way to probe the calmness of the final black hole. So that's just saying it's determined by mass and angular momentum. So other things are where we can look into that are the Emery signals. I already said this is deviation from the metric. If you go around a long number or a high number of times, do we see anything in the LIGO sources? Maybe we see deviations from the predicted merger time or something like that. But we need relatively high signal to noise, and the proposers have coined the golden binaries and golden Emerys there. And as usual, There should be an extremely in here, but maybe a handful per year. So, but this is pretty much the only way you can ever test that. Expansion rate of the universe. This is something a little bit exotic as well, but extremely cool. So, gravitational wave signals are extremely simple, right? So they only depend on the redshifted mass of the sources and their spins and the distance. So, in other words, and the mass effectively determines the frequency and the amplitude. Now the amplitude also depends on the luminosity distance. And that's it. There is no additional reddening. There is no dust scattering that reddens the spectrum. Nothing like that. It's just that. So if you see the signal, you can immediately say mass of these things and luminosity distance. Now if you know the luminosity distance and if you know the redshift, you know Hubble's constant, right? And you know Hubble's constant in a completely independent way, because you're not relying on electromagnetic radiation to give you the luminosity distance. You still rely on electromagnetic radiation to give you the redshift, though, because black spectral lines really don't work here, so you need to have electromagnetic counterparts. And that's a little bit of the problem, considering our lousy sky resolution, to identify the host galaxies of these mergers. However, there might be some way to beat that down with statistics if we detect enough, but there is no modeling of any interstellar media required, which these days sort of pollutes a bit the estimates. And now I'm cheating a bit there. Gravitational waves follow the same geodesics as light does, so they suffer from weak lensing and from strong lensing, but strong lensing doesn't happen that often, but weak lensing does. Right, so in essence, they flicker. And so you need to take care of that flickering, but even with the flickering where the amplitude is slightly uncertain, because the signal that comes to you might be microlensed, still a few percent accuracy is possible, which is commensurate with the current electromagnetic measurements, but obtained in a completely independent way, which, considering that we are now in a state where the error bars of the different measurements are smaller than the distance between the scatter of the different measurements, might be a good thing. Now, stochastic gravitational waves, I'm tempted to glance over that because not only it's rather exotic, I know the least about that, but sufficient to say that if you know how the cosmic microwave background started, then you can imagine that there might be a time where the gravitational waves decoupled and the universe became transparent, so the density of the universe became low enough that gravitational waves were not completely reabsorbed every time. I mean, this is a mind-boggling thought about the density, how dense the universe has to be to actually reabsorb gravitational waves permanently. So clear that is a different time scale, so tera-electron volt instead of electron volt, roughly, in terms of energies. I have one thing I point out here. You need to assess your instrument noise. You can't do that very well, because if you do that with electromagnetic radiation, you just close the shutter of your telescope and you look at the dark current of your detector, right? Now, this is a bit difficult here because you can't shut down the instrument, you can't block gravitational waves. So we need to have another way, and I'll talk to that a bit later. The unknowns, I'll leave you to that one. The unknowns are called the unknowns for a good reason. But keep in mind, the very first source, actually the first, the second, and the third first sources we saw in LIGO were something where nobody had a clue that these sources existed. Right? So 30 plus 30 solar mass binaries were pretty much nobody had them on sort of on their wish list. And I'm sure we'll see something like that with the space-based detector Just because we think that we understand general relativity very well doesn't mean that's actually true. So, I want to conclude that by just hammering home that we have a very solid science case. We're far from the situation where this is an add-on on a LIGO-based detector, right, or LIGO-verbal ground-based system. It opens up completely different science. It uses the same radiation, but that's about it. And so it's both complementing in terms of the stellar-sized black hole, the 30 plus 30 size black hole systems, but it also does completely different things as well. It opens the low-frequency domain and allows us to observe the very early universe. Now, the next talk is, I will tell you how the mission actually looks like. So, let's fill the next hour till the coffee break with, let's say, a mission design for a space-based detector. And this will a little bit run into the talk after that, where I show you things we actually have flown now with LISA Pathfinder. So it's very difficult to break that up in two talks, as you will see. But nevertheless, let's go there. And so this is just a quick reminder from the talk before. Why do we go into space? Well, because we have that seismic wall, right? So I told you, difficult to measure things at below 1 Hertz with ground-based detectors. So what do we do? Well, it's very simple. We take LIGO, which is on the left, and there it is, right, and put it there. Well, that was easy. The problem is we have to think a bit before we do that, because complexity is a problem, right? Now this is not even sure if this is the current optical design of LIGO, but probably it's pretty close to it. And you see all these wonderful things here, right? So you see, particularly you should see something like 800 watt hitting the beam splitter, 100 kilowatt circulating in cavities. So these are all, for spacecraft engineers, these are all extremely scary numbers. And if you look at the number of components there, and mirrors and all that, and the things that are not plotted on there, all the control loops, this is even more scary for not only space engineers, pretty much for everybody. And if you look at this, as you might recognize, I think this is inside one of the ham chambers, and this is one of the two labs, and I don't know which one, probably Hanford. And the size there is about, the blue things are about, I think, the height of a person. So, if you want to put that into a spacecraft, you have, let's say, issues with your launch mass. So as a general indication, typical things we can lug into orbit are about 10 tons. And that's a stretch, right? So the times of the Saturn V, which could do much more, are long gone. The shuttle isn't there anymore either, and all the systems we have at the moment are, I think if you want to put up 10 tons, you have to pray a bit. So we need to do something different there. We cannot put something of LIGO's complexity into orbit, but fortunately we don't need either. Because a lot of the complexity of LIGO is dedicated to combating seismic noise and to reach high sensitivities. Displacement sensitivities, that is. And I told you, low frequency detectors are typically not as sensitive. Where LIGO goes to attometers, we go to picometers, which is a factor 10 to the 6, which makes things a hell of a lot easier. Or so you should think. So what do we do? Well, go back to the beginnings, choose the simplest possible system. What is the simplest possible system? Well, you learned earlier, last week or something like that, in the lectures about general relativity, that gravitational waves affect geodesics. So the path that light travels. And actually this is how we write it down, right? You see that the ds squared equals 0. So all we need to do is to measure the distance between two fiducial points in space. Right? You have one here, you have one there. If you measure the distance between them very precisely, you're done. And actually it turns out you're not interested in the distance either. You're only just interested in the change of the distance. And then there are people who say, actually you're not interested in that either. You're interested in the change of the distance, so the acceleration, because gravitational wave imprint tidal forces. That's the same way of looking at things. I mean, everybody can differentiate and integrate, so there's no need to argue endlessly about if it's acceleration or distance change. You know, we all know how to handle that. All the mirrors, the cavities, all the control loops that LIGO employs are, and I use that a bit provocative here, a technical convenience. You need that to increase the sensitivity and to combat seismic noise. If you were able to just take 2 points in space-time and measure that, you would be fine, right? So, there's one hitch, that one. You need two measurements, because you need to have a base for comparison. Again, that's a little bit of a technical inconvenience that you have, because you don't have a length standard or a time standard or a frequency standard that's good to 10 to the minus 20, which you would need to measure effects of 10 to the minus 20 on the way light behaves or light travels. So the best way we know how to do that is to build two of those systems and compare them against each other. And if you have to be clever, you realize that you can't put them next to each other, because then the gravitational wave affects both in the same way, and that's nothing one. So you put one into an angle to the other, and then you make use of the quadrupole nature of the gravitational wave. So, by the way, ultra-accurate clocks, if you had clocks with 10 to the minus 20, 10 to the minus 21, we only would need one stretch, only one distance, and compare the light with the local clocks on each spacecraft. But we are 3 to 4 orders of magnitude away in the lab, and about 6 to 7 orders of magnitude away in space. So with the accuracy of clocks. So maybe in the dim and distant future, clocks are the way to go. At the moment, they're not. However, the other thing that I like to point out here, hey, look, no hands, no beam splitter. Again, the beam splitter in the interferometer is a convenient and very, very clever way to compare the phase of the two light fields coming back from two different directions. Right? It's wonderful, it works. But if you look into that, it's technically not necessary. If you were able to measure the phase of the light independently, you could do that, and you write down the numbers, and you go back to your computer and let the computer do the comparison. So you do sort of a post-the-fact differentiating of the phase. Yes, you lose sensitivity, but we will see that's probably not a problem for space-based systems. So, this is what I already said. We are sacrificing with all these things, so go to the simplest possible system, don't care about laser power and all that. This is just sacrificing, shedding sensitivity left, right, and center, right? So, but ground-based detectors have sub-attometer performance, and mostly at some frequency range, they're limited by the shock noise of the hundreds of kilowatts they have in the arm cavity. Now, space-based detectors, 100 kilowatts, you can forget that, right? You'll never get that with current technology. So the typical laser powers you employ on a spacecraft of the order of watt. Now, if you do that, you say, well, maybe we can't do attometers, but maybe we can do picometers. And if you do the math and say, you know, I send out a laser beam of 1 watt and let it travel for a couple of million kilometers and pick it up with a telescope about this size, then I get about 10 to the 10 photons or something like that, which gives me a shock noise of 10 to the minus 5, which means picometers. You know, 10 to the 6, 10 to the minus 6 is the wavelength 10 to the minus 5 of that, just a couple of factors of 2 pi that I hand waved away here, picometers, right? Now, but if you have picometers and you want to have a strain sensitivity again of 10 to the minus 20-ish, right? So I say tenths of picometers, so maybe you have 10 to the minus 11 displacement sensitivity, and you want to get to 10 to the minus 20 strain sensitivity, you need to have about 10 to the 9 meters. Well, simple. Put the mirrors or the end stations or the masses or whatever you want to call them about 1 million kilometers apart. Well, fortunately, that's not a problem in space. It has in space, lots of it. So if you can one satellite in orbit, you can put more than one satellite in orbit, not a problem. On ground, you struggle with arm length of more than 10,000 kilometers, but and even that would be quite a tunnel. But space, not a problem. There's another advantage or another trick we can play if you forgo the beam splitter. If you kick out everything you learned from Lurgis about quantum mechanics of your detector and say, I don't care about that. At picometers, quantum mechanics really doesn't play a role, right? And by the way, we are drowning in the shot noise of my couple of hundred picowatts that we give you there. By the way, you hear me saying picowatts and picometers and all that. There is a term that a friend of mine coined, the former project scientist in the United States at NASA. He termed the phrase picophobia, which is the irrational fear of large negative exponents. And then shortly after that, the femtomania came up, which is the incredible urge of making those exponents even larger. And you will see later why we have that, because when we first walked into a room of engineers and told them about picometers, they looked at us a bit as if we had a communicable disease. And now picometers we are all fine with. People flinch a bit when we mention femtometers, but you know, time will show. So here's the other trick we can play. We give up the idea of beam splitters. So we just measure the phase, or if you want the arm length, to picometer precision. Now if you do that, you realize that if you delay your data streams accordingly, let's say you start out with over here, and the light goes up and down, and then electronically you say, I delay it by some arm length here, you can shift your data streams in such a way that you effectively construct yourself a white light interferometer. And why is that important? Because you know that white light interferometers are insensitive to frequency noise. You want to measure a delta L over L of about 10 to the minus 20. If you had a unequal arm interferometer, then your frequency noise couples in at roughly the same level. So you want to have your frequency noise on the order of 10 to the minus maybe 15, 16, 17 or so, which is a challenge. Or in other words, maybe impossible. So what you have to do is you have to make your interferometer by cleverly combining your data streams insensitive to frequency noise. Well, once you've done that, your laser engineer comes back from the coma you just sent him into and says, okay, you know, that sounds still insane, but borderline doable. And then you say, well, hang on a moment. If we actually have the way to construct ourselves a white light interferometer, can we construct other interferometric geometries or topologies as well? And this goes back to this idea of the null stream I mentioned at the bottom of the last lecture. I said, well, to assess stochastic noise, which has no clear time signature, you really have to have your instrumental noise very well under control. The only way to have your instrumental noise under control is to measure it. Now the problem is, in our business, you cannot measure that without somehow switching off the gravitational waves, Well, turns out there is an interferometer that you all know, which can be made insensitive to gravitational waves. This is a Sagnac interferometer with zero area. So effectively, a twisted Sagnac, which looks like a figure 8. That is at least sensitive, has no sensitivity in the low frequency limit of gravitational waves. As soon as the gravitational wave frequency comes into the range of the round trip time there, things change. So, but what we can do is we can say, well, we measure everything anyway. By the way, you see the 3 arms here. I haven't talked about that, but we realized at some point, very early in the game, that if you have to have 2 measurements, 1, 2, and if you can easily have a third one as well, if you put all these into one satellite here, as long as you have 60 degrees in between. So the third arm is, for our purposes, a nice convenience, and it helps the science a lot because of exactly that effect. You can now construct yourself a Sagnac mode left way around and a Sagnac mode counterclockwise. You can take the difference of the two, and any gravitational wave signal of suitably low frequency should vanish. It does. The only thing that doesn't vanish is the instrumental noise, which is good. You just found a way to switch off gravitational waves, like you block the input aperture of your telescope and look just at the dark current of your CCD. This is a nice way to look at the instrumental noise of your detector. Not exactly a dark current, but it tells you a little bit what the noise level of your detector is. Very, very useful. Not something which is, it's not something where the mission is dead if you don't have it, but it's very, very convenient. It's a great diagnosis tool, a diagnostic tool. It's needed for cosmology and stochastic signals. At least it makes life a hell of a lot easier in the stochastic regime. And now, let's look a little bit into how we define those endpoints. I told you all we need to do is we need to measure the distance between 2 points in space. Well, how do we do points in space, right? We need to have something there. And how do we define them? Well, theoretically it doesn't matter, right? You could say, I take this point, I take that point. Now your engineers again look at you slightly funny and say, hang on a moment, what do you mean? Take a point here, take a point there. I need something there, right? I need to have a mirror, a point in space, a little crosshair, whatever. So, to measure in between. So, practically, we have to figure out how to do that. And, well, what we want to have is as little as non-gravitational forces as possible. And again, this is nothing which is fundamentally needed. It's just that we know the best way of keeping forces to know very well which force is acting on something is to make that force 0. A 0 is always a nice number. And so we try to keep them as low as possible. 0 is not possible, but as low as possible. And every picometer here counts. The best way of doing that is to put it to free fall, which is another word for switching off all non-gravitational forces, right? So, another bright idea you might have is to say, hang on a moment, these things are disturbed by forces. Let's talk about which forces there are later, but assume that there are forces around, but what really disturbs our measurement is acceleration. So, and if you have forces, you want to get to acceleration, you divide by the mass. So the best way to go is to go as heavy as possible, right? So you take a lump of gold. Gold is shiny, right? It's heavy. And the lump, for practical purposes, are cubes. Many discussions about that, but it turns out that we can machine straight faces much better than we can machine curved faces. So spheres are much more difficult to manufacture and to control. It's about 2 kilograms. It's about 46 millimeters cube, so about here big. It is actually an alloy made from aluminum, gold and platinum. And this has a practical purpose. If you mix these two in the right ratio, you get zero magnetic susceptibility. Well, that didn't work out. We are not at 0, we are 10 to the minus 5, but that's still a factor of 10 or so better than everything else that you can buy. And unfortunately, it's not an alloy, it's a pseudo-alloy, which means that it's not stable at room temperature. So it has to be formed at, I don't know, 800 Celsius or something like that, and then effectively shock frozen in an oil bath to lock in the crystal structure. And if you leave it for a couple of billion years at room temperature, it will sort of unmix again. But that's not really a problem. But it is a problem in material science to make that really homogeneous mixture and not platinum, little platinum bits next to little gold bits. Right? So it is, by the way, it's coated with gold. This funny thing here, the aluminum gold platinum alloy, is a very, very dull gray. You would expect that for the price you get something shiny, but you don't. It's really dull, right? So, and the gold coating has an interesting property, which I will tell you later when I come to the stray forces in RISA Pathfinder. It minimizes a certain kind of stray force. And you see, this is, I don't know, I think this is a euro coin, not a new pound coin. So, there you go. So now we have the endpoints, these masses. Now we have to put them into the right orbit to have some sort of triangular structure, right? Now that's easy, there it is. I've been asked this question yesterday night by one of you gentlemen there, and I said I will explain that today. So this is a non-to-scale sketch, quite obviously. So this is 1 AU, like the orbit of the distance of the Earth to the Sun, so that's 150 million kilometers for the non-astronomers out there. The inter-satellite distance is about 2.5 million kilometers. They form an equilateral triangle that is tilted against the ecliptic by 60 degrees. And it is sort of 3 weeks or so behind Earth on its orbit. And it looks like that when it evolves. So you see, you can imagine that the upper one is further out. So you know things are further out, they are slower. If they are further in, they are faster. So the top of the triangle that is further out will slowly lag behind and sink below the ecliptic. So in other words, this whole thing is counter-rotating. That's just as it is. Now, how do we get there? This is an interesting thing for those of you who have to set exams for students who just heard something about Kepler's laws. It's exceedingly simple once you know what you're doing. As long as we ignore the Earth. So if you assume we have just the Sun and the constellation, there's a set of occasions that the name of which depend on which side of the Atlantic you're studying. In the US, they're known as Clohessy-Wiltshire equations, and in the rest of the world, I think, they're called the Hill equations, and you find them as Clohessy-Wiltshire Hill equations in Wikipedia, quite fittingly. And this is just a linearized Kepler's law in a co-rotating coordinate system around a certain point here. You see the differential equations become exceedingly simple. They're just simple coupled in 2 dimensions, so you can already squint a bit and see that, oh, there's a 2 and a 3 and a square, so it's probably 60 degrees. If you take the cosine of and the sine of 60 degrees, and they move on the circle. So that's very simple. If you want to look that up, if you type that into Google, I think there are a couple of MIT open lectures coming up, which are very good. It's very nicely written there. The triangle is always constant. It's not a fixed constant. It's not a static constellation. The arm length changes a bit, and it's proportional to L over A. So, you know, we are at a factor 40 or 30 to 40 away from the astronomical unit. So this is about a few percent, and L squared over A. The arm length changes. So The fractional arm length changes is sub percent. The angles in the triangle change a bit as well. It doesn't stay at 60 degrees, which is an interesting challenge for the engineers. The center of mass stays fixed with respect to Earth. That is a nonsensical statement because we're ignoring the Earth for the moment. All I want to say with that one, it just moves with a constant rate. Now the problem is the Earth isn't, as you know, because the Earth orbit is elliptic and not circular. So it comes closer to the Earth and moves away. And that makes it comparatively dreadful to the point where you can't do that analytically anymore, you do that numerically. But the upshot is that as soon as you include the Earth and the rest of the universe, mostly Jupiter and Saturn and the Moon, then energy is pumped into this constellation and the wobbling gets stronger over time. Also, the constellation drifts closer to the Earth and drifts out again. The thing to look up there is horseshoe orbit. It's a very interesting thing as well, but goes a bit beyond the scope of that talk. Tidal forces pull of the Earth's pull on the arms, and so eventually the whole thing becomes volatile beyond the point of which we can actually use that for gravitational wave detection. Because if things move around, you see a Doppler effect. So the light coming back has a different frequency. Your AD converters only can cope with a certain frequency shift and all that. So we need to keep that under control. Fortunately, if you go further away, then the influence of the Earth, of course, is smaller. But if you go further away, you have difficulty to talk to the constellation. It's easy to underestimate 55 million kilometers in terms of communication. That's very far away. So the bandwidth you get is about 150 kilobits per second. That's not enough. It's not a lot. So, as I said, communications is an issue. Lifetime is an issue. So it takes a while for the Earth to disrupt this constellation beyond usefulness. And that depends also on how close you are and where you start. So the upshot is this whole shebang there is within 19 to 23 degrees. And the 2.5 million kilometers and the 4 to 10 years lifetime, it's a compromise, as everything is if you go into space. There's usually no clear yes or no. As I said, it's a practical compromise. You want to keep it close enough. I said that, adjust everything for mission duration for up to 10 years. So you set up a frigging big optimizer that optimizes these 18 parameters here, the 6 state variables per spacecraft. And you have some fun with numerics and learn a lot about optimizing algorithms. And at the end, you don't know much more than before, but at least you have a solution that works. So here's a reminder, because this is a question we often get as well. The distance between the endpoints between our measure don't have to be constant, not at all. They are in LIGO, because the way the vacuum system is built. The direction of that isn't constant, of course, because the Earth moves. But as long as the variations in the frequency band of desire is small enough, so I put here 0.03 millihertz, so 30 microhertz to a hertz about is small enough. Now it turns out that all tidal forces here act on timescales of about 10 to the 7 seconds, which is 3 to 4 months. So we are safe. And there is no need for formation flying. We don't need to control the distance between the spacecraft. We can just let them go. Right? If we start at the right position, with the right velocity, everything will be fine. Formation flying would not be feasible with the kind of engines we have on board. So formation flying is just the, keep everything constant and all that. So, as I said, the normal constellation counter-rotates now, fine, but there's an equivalent constellation that doesn't look like that, but looks like that. We never plot that because it looks kind of sad, and we don't want to look sad, so we always look like that. But that one co-rotates, and there is otherwise zero difference. Just in case some of you stumble across that and say, hang on a moment. Now, back to freeform.
Excuse me?
Yes.
So I was thinking of why not to put just things in stationary orbit around Earth and just shoot lasers around Earth. But is the problem essentially like laser power versus arm length, or?
No, but the problem is that if you put it into the Earth orbit, well, the easy way of thinking is you can't. But the reason for that one is that the Earth is not in a circular orbit. This one here is a circular orbit, right? The center of mass of that constellation is in a circle around the Sun. The Earth is not. The Earth has eccentricity. So what you will see there then is a equivalent, if you go into the co-moving coordinate system, I don't have that plot, but you would see the Earth doing that in the co-moving coordinate system. It does that anyway, right? But here it's 1.7 million kilometers away, and if you put it here, it's 55 million kilometers away. And the 55 million kilometers already disrupts your constellation after 10 years. So in other words, if you put the Earth in the center of that one, your mission is over after a few months. The effect of the Earth, and we haven't talked about the Moon yet, of the Earth is too disruptive. And this is because the Earth is not on a circular orbit. The Earth orbit has eccentricity.
No, but what if we put them into like stationary orbits around Earth, like very close? We have much smaller arm length than but like.
Well, yeah, then you have 36,000, 40,000, 50,000 kilometer arm length. Then you need to go down to, instead of to picometer, you need to go to femtometer, which your interferometer is happy to give you. Your free fall conditions are not. You cannot bring your forces down further than that. So, I mean, there's one part of the compromise I haven't talked about, and this is how to apportion the noise. I will show you that in the talk after the coffee break on LISA Pathfinder. So, okay, we want to protect these things from, but that's a nice lead into what I'm trying to tell you now. It's the free fall issue. Right? Now, what do? We want to keep our endpoints, or as we also call them test masses, shield them from non-gravitational forces. Again, that's just a convenience. You don't need to do that, but that's the only way we know how to know about the non-gravitational forces, to make them as small as possible. We demonstrated that on LISA Pathfinder, and this is a cartoon that I borrowed from presentations I usually give on LISA Pathfinder. So this is my test mass. It's in free fall. You don't see that, but you're co-moving, so everything is in free fall there. The problem is that somebody had the right idea to switch on the sun. And what the sun does, it shines on the test mass, and radiation pressure with the reflected surface is 2 times the power over the speed of light, so it pushes that thing away. And you know, that was the issue with the free fall, because we have now clearly a non-gravitational force on it. And you could model that, but that's extremely, extremely difficult to do. The obvious thing is, hey, you put a box around that thing, right? So now the sun shines and pushes the box away. That's, in principle, a great idea, only eventually that will happen, and the box is pushed into the little test mass, and free flight is over again. So, well, you know, what we of course do is, you know, an engineer looks at that and say, you guys, you're stupid. You just have to measure the distance between your test mass and your satellite, like that, somehow, right? And if you now push, you can measure, and you attach a thruster, and when the sunlight pushes, you fire the thruster, and you push back. And everything is good, right? Now, that's free fall in a nutshell. That's very simple. You start wondering why it took so long, right? Now, there's another cartoon I have to make. The problem is that LISA has 2 test masses per spacecraft, but we are only after 1-dimensional free fall, so only in the direction of the line of sight with the other spacecraft, right? Across, we really don't care because we don't measure, we just measure that way. And there's a little cartoon that shows you that is actually possible. You know, you move the spacecraft and the other test mass is in the center, but you can push that orthogonal to your measurement, and then you recenter the spacecraft, and you iterate, and now you're at a much smaller separation than you had before, and you know, you could, in principle, you could iterate that, or you can talk to your engineers and they design you a circuit that does that in one step by doing it cleverly. But you only ever have to move your test masses in orthogonal ways. And so the satellite, in a way, the satellite here does the impossible. It moves in two directions at the same time. Right? But that only works because we can act on the test mass in orthogonal directions. We, as I said, we demonstrated that in Pathfinder, and I'll leave that after the coffee break. Now, if you go to space, you typically, the engineers ask you for requirements. I mean, you can't tell them, I want to measure black holes. You have to tell them something about, you know, how well do you need to measure, what is your uncertainty, and all that. So we decided to say, well, we want to measure the displacement to 10 to the minus 12, actually 10 times 10 to the minus 12 meters per square hertz. So 10 picometers. This funny shape factor here simply tells you that for low frequencies we don't care much, because low frequencies we are dominated by acceleration noise on the test masses. And acceleration, you know, is 1 over f squared times the displacement, or f squared times the displacement, because we have to differentiate twice. So intrinsically, acceleration noise drops down like a stone at high frequency. So for the acceleration noise, we make a similar assumption where you say it's below 3 times 10 to the minus 15 meters per second squared hertz. And again, funny shape factors that tell you at high frequency we don't care. At very low frequencies, we are actually a bit more careful and say, well, maybe it's worse there. Details on that in the Pathfinder talk, and this is why I said it's very difficult to separate the two, but I want to tell you a little bit about the other subsystems on LISA as well. So if you now start wondering what is this about acceleration noise and why that is a problem, I'll show you after the coffee break, right? It's a bit of a make sure that you actually come back. So the other problem we have to send a laser 2.5 million kilometers. You can't just do that, right? Laser light diverges. And you know that the divergence is about lambda over d. Lambda is the wavelength, d is the diameter of your optics, and there is an insignificant factor in front of it of order 1. Right? So that's a theoretician's idea about diffraction. Actually, yeah, I know it's 2.44, but never mind. So you need about 30 centimeter telescopes to focus the beam to a point where you can have a useful amount of light on the other end. And what is the useful amount of light? Well, you need to detect enough photons to be reasonably well below under that 10 picometers budget you've just been given. And that turns out, if you do that, you know, if you send out 1.5 lasers, 1.5 watt, with those telescopes you receive about 800 picowatt, which is plenty to make that not an issue anymore. So you just crossed off one worry, which is you have way too few photons to actually ever measure the change in distance to better than 10 to the minus 5 of a wavelength. The problem here is those of you who have some experience in astronomy, observationally, you know that normally telescopes are imaging telescopes, either through an eyepiece into your eye or via directly on a CCD, and you look at nice pictures and you expect these things to be crisp and sharp and without much defocus to the edges and all that, same as you buy an expensive camera lens. Now, these are not our telescopes. We couldn't give anything for imaging quality. We want to transfer the wavefront, which means that we need to know how the wavefront propagates through the telescope, which is a design challenge and a cultural challenge to normal telescope designers who are not used to this kind of language or this kind of thinking. But, you know, this is part of the business to make sure that people actually understand what you want. Here's the caveat. I already told you they change the 60 degrees, don't stay at 60 degrees. They vary about 1.5 degrees over the time scale of the mission, periodically with about a year or so. So they must be articulated. And you see this is a single telescope here. The green one is the light. Yes, we use infrared light, but they still depicted the light in green. And then this is the outside view, and you see those two telescopes in roughly 60 degrees. And somewhere in there, the little green stub here, it's a pusher that can change the angle between the telescopes. So these telescopes on ground have a mass of maybe a total of 100 kilograms or something like that when everything is said and done. So we need to move them around on the satellite to cope with this. The lasers, I just said, near and yak, same as everybody else. Really for convenience, it really doesn't matter. But when we started, this was a nice laser, still is. About 2 watt delivered to the optical bench and then 1.5 watt out. The rest is sort of stripped off and scattered and used for different purposes. You bring these things to the bench with fibers. I said before that we form white light interferometers, so therefore we don't care about stability. That's only half true. We still have relatively high requirements, a few hertz per square root of hertz at around 10 millihertz. That's still challenging, but doable. Power stability is an interesting thing because we measure the position of our test masses with respect to the satellite. I'll show you that in a second. Interferometrically, they are free floating. We don't touch them, but we just shine light on them. And if we vary the power of the light, we have a fluctuating force. So we need to have some stability on the power, but that's doable. So why do I say we measure the distance interferometrically? Well, what we don't do is we do not measure test mass to test mass, because it turns out that is technically very, very difficult. So what we do instead is we measure the distance of the test mass to a reference point in the satellite, and we measure the distance between the satellite and the satellite, and we measure the distance of the other satellite with respect to the test mass, and we add everything together. Now, if you work in the ground-based community, this is the moment where you despair, because, oh God, you know, instead of doing everything nice, they add 3 times the shot noise penalty. Yeah, but we don't care, right? The shot noise of that one here, we use a milliwatt laser for that one. That's so much lower than the 800 picowatts or so we see here. So everything is dominated by that measurement anyway. So if you add a little bit of noise, it really doesn't matter. As I said, there are advantages of working with low light levels. Everything is shot noise limited, and you don't have to sweat the quantum stuff. Here's a nice sketch, not exactly up to date. I should have done the Glasgow, University of Glasgow template here, but you know, imagine there's a University of Glasgow logo up there, because I borrowed that from them. So this is the top. The optical bench has 2 sides, as every optical bench has. In the lab, you typically, for convenience, populate the top side because it's so difficult to go on the other side, but in space you don't care. And we are space limited, right? You see it's about 50 centimeters diameter or so. Other critical things that you have to think about if you go into space, and this is, you know, the top 0.01% of a list of things you have to worry about. But they're interesting things because sometimes ground-based experimentalists have difficulties to think about these things. So you want to have thermal stability. So we call that, it's a thermal noise, but it's not the thermal noise that you heard about, which needs to have this fused silica suspension systems and ta-da-da-da-da, all that. No, it's much more down to earth. You want to avoid the expansion of the material. Right? You want to measure picometers. If your optical bench expands by nanometers, you're toast. Another thing that people rarely think about is that if you have transmittive optics, like a beam splitter, like a window, optical window, like a lens, then CTE is the least of all your worries because it's only a few millimeters. What really kills you is the change of refractive index with temperature. It should have been a capital T, yes. It's not m dot, it's dny, the temperature. So once your temperature changes on the spacecraft, your refractive index changes, and which means your optical path length changes, and this is what you measure. Fortunately, there is no true thermal noise issue, so we don't have to worry about suspensions that are very low loss and all that. Gravitational balance is a great thing. So I have my test mass here, right? That's floating inside the satellite. And let's suppose the satellite is heavier on this side. So the test mass say, oh, I like to go there, right? The satellite says, yeah, well, you're well allowed to do that, but I have to compensate for that. And then you have this carrot on a stick problem that you very quickly are drawn off your orbit. So the way you do that, you have a mass model of your satellite where, you know, every nut, every bolt, if you're close to the test mass, the number of threads on your nut and how they are shaped are in. And then when people put the spacecraft together, they use a very high-tech process. So one of the things they have to do is they put the harness on. The harness is a fancy word for cable. So you put this cable on your spacecraft structure. And as I said, it's high-tech, right? So use cable ties for that. The best we have, so you use cable ties. And the people who put on the cable ties were under strict orders. Before they put on the cable tie, they put the cable tie on a scale. They put the cable tie on, they marked the position where they put the cable tie on in a spreadsheet. They pulled it tight, and then you know there's this little stub standing out from the cable tie, and you cut it off. And you put that on the scale as well, so that you know exactly how much mass you put there. And that sounds like an insane procedure. It is. And you know, who knows? I mean, you're not standing next to them and find out if they actually did everything right. But it turns out they did that extremely well. So on ESA Pathfinder, and but this is an issue. You need to take care of that, which brings you in an interesting position with respect to fuel usage, spacecraft control. You need to somehow control your spacecraft, and if you have 3 satellites and you know, it's like an operating system, running it is simple, getting it to boot is the problem. It's here the same. You need to acquire the constellation, so you first have to have the laser links before you can actually do something with them. Commanding bandwidth, 60 million kilometers is about 400 second turnaround time, right? So that's 7 minutes or 6 minutes and a bit. So one command send, a little cigarette, and then the next command send. The data rate is very, very low, so forget your terabytes per day. That's not going to work. And data analysis is an issue because we're in a signal-saturated environment, which means we have signals, lots of them, and that's nice until you realize that's a really interesting challenge to make sure that you can actually get them out. So here's, you know, there will be a test at the end. So there are all the requirements, top-level requirements. Imagine that behind each of these lines here, for example, the communication needs. This is a 300 megabyte per day, which is about 100 and something kilobytes per second. Behind that are hundreds of pages of breakdowns where you say who gets what and how do we do that. Power in space is an issue. You only have solar power, you're under 60 degrees, so you're illuminating not under 90 degrees, so you lose power there. Mass is always an issue. As I said, you can't carry too much into orbit. Charging of the test mass, I'll tell you in the talk after the coffee break. What else is interesting here to say? Probably all the rest is just things that are meaningless if you're not working in the field. Magnetic field is an issue, simply because, not because it's a particular strong force, it is just a nasty thing to model, and an even nastier thing to validate your models, right? If you model things, that's already always nice. I mean, you come out with a nice shiny solution, right? And you can plot that in gazillions of colors in pseudo 3D, and everybody said, oh, that looks cool. The question is, has the result of the model anything to do with reality? And the way you typically do that is you model, you get a prediction of how something looks like, and then you go and measure and see if actually the things coincide. Now, magnetic fields are difficult to measure to the right precision and with the right spatial resolution. And this is, magnetic probes have a certain size, and magnetic fields are in general very, very annoying things to have. So you try to get rid of them as much as possible, which of course doesn't work, because at the end the sun is shining on your spacecraft and creates electrons in your solar array, which go to your power converter, and the current is going. So you have to find a useful compromise. So the next talk will be about LISA Pathfinder, where I touch upon a bit more about the nasty details of the technology and how we actually do things. Another 5 minutes or so for the coffee break. If there are questions, I'm here to answer. Good. Yes.
Why can't you recapture the test masses and the space after?
Yeah. Okay. So the question is, how do we capture how do we hold the test masses? The first question is, why do we have to hold the test masses? And I show you a little picture later how do we do that. But just briefly, you need to, before you're in free fall, you're not, and you're suffering something like 70 G acceleration during launch. And you need to keep the test masses where they are and not rattling them through the spacecraft. So we have a particular mechanisms for that caused us a lot of grief and time to make sure that we can hold the test mass during launch and release them on orbit in the right place with low enough velocity so that it doesn't rattle around. I mean, I'm not telling too much, as we failed in doing that. It rattled around at the end, but just a bit. It wasn't really a rattle, it was more like a anyway. Yeah.
Have there been any challenges dealing with either like fuel slosh to thrusters or even meteorites or micrometeorites?
Yeah, well, micrometeor, let me answer you the second one first, because I won't tell about that in the next talk. Micrometeoroids are an interesting issue. We saw a handful of impacts on LISA Pathfinder, where we are pretty sure that they are micrometeoroids. If you do the calculations and assume reasonable sort of relative velocities, then you should be able to see things down to nanograms hitting the spacecraft. The problem is identifying them in the noise. So yes, they are there. They will hit the spacecraft. They don't look like gravitational waves at all. So that's fine. Still, in Pathfinder, we had a couple of events where we were hit and the electronics said, oh boy, right, let's sort of keep a close hold on the test masses, and interrupted the science data taking for that for a couple of minutes, because there was enough momentum transferred to the spacecraft. Femtometers per second or picometers per second is enormous velocity. Then you really, you notice that. The sloshing of the fuel is no issue, because nitrogen doesn't slosh. We use cold gas. The gravitational balance issue of the fuel is an issue. If you deplete your fuel, which you do, you expel nitrogen, then the nitrogen leaves the spacecraft. And if your gravitational balance was designed to be met with a certain fuel level, then you're off before and you're off later. And we have nice measurements. I show you in the next talk how that works. And yes, you can see it. You have to compensate for that. It's a noise source. Again, it doesn't really look like gravitational waves, fortunately. And you know very well what you're doing, because of the mission control people can exactly tell you how much fuel they used, how much momentum they transferred on the spacecraft, and all that. And then you look at your own data and realize that you can do it better by just guessing the gravitational balance. Okay. Yes?
What was the duration of LISA mission?
So we designed the mission duration of LISA. All the design parameters are for 10 years. For 4 years, except for the fuel or the cold gas, which is for 10 years. So the idea behind that is we build everything so that it lives for 4 years with a reasonably high probability, and we pray for the next 6 years. I mean, typically space missions last very much longer than they're designed for. So if you heard the expression the bathtub tube, the bathtub curve statistics is things in space die early or late. So if it survives the first 3 months, it's typically safe for many years, and then eventually it dies. But it's not like a linear decrease. So in a way, if you design for 4 years, you have your redundancy in place to deal with these things that go pear-shaped after 2 months, and then hopefully everything will be fine. And the only consumable really is the fuel. Yeah.
I was wondering what the effects of like solar wind, solar flares would be.
Ah, boy, yeah, interesting question. Depending on how they work, anywhere between an annoyance and buggery. So what the solar flare does is effectively it kicks charged particles in your direction. It charges up your test mass, so you have to discharge it. And we do that with UV light. It has a certain amount of capability to discharge n numbers of electrons per second. If the solar flare deposits more than that, you end up with an interruption of the measurement mode, and you have to wait until your UV lamp actually shines for long enough to kick enough electrons from the test mass to equalize the potential. Magnetic fields are an issue. So if a magnetic field changes drift over the spacecraft, you see that. You see that in the magnetic sensors on the spacecraft, and you see it in the measurement. Nothing we can do about these things are not lasting forever. If they interrupt some very, very cool measurement, we can all be very disappointed, but absolutely nothing we can do about it. They will happen. You make sure that the spacecraft survives. If your measurement is interrupted, so be it. Right? But we saw in LISA Pathfinder a couple of effects of rapid magnetic field changes. They did the predictable thing, like changing forces on the test mass slightly. Yeah, we deal with that. Okay? Coffee break, right? Okay, let's go to LISA Pathfinder. As I told you before, this is where I try to give you some more insight in the technology, and we remind all of you who have not been following that mission over the last many years, why are we doing that actually? Why do we do LISA Pathfinder? Typically, space agencies don't do Pathfinder missions because usually they're considered to be too expensive for the stuff they're actually showing. LISA Pathfinder was very expensive as well. Still, we did it. Probably because at some point people realized that now we have spent so much money and effort, we can just go with it. But was a demonstrator for the critical technologies in LISA. The critical technologies here really means free fall. Right? If you talk to people 10 years ago or even 5 years ago, they always said, oh yeah, great idea, LISA, brilliant science, but really this free fall stuff, that's never worked. So the idea was to test the free fall of the, the test masses. Also, the next thing, a little bit down in criticality because it's only, quote unquote, an engineering problem. By the way, when you ever hear that sentence, right, oh, this is only an engineering problem, like head for the horizon, because this will cost you years of your life and a shitload of money. The only engineering problems. So, flying actually the satellite around the test masses, right, doing the measurement, actuating the thrusters and all that. The micro-Newton thrusters itself, so what do we actually use? I mean, the question was earlier, do we have a problem with fuel sloshing? No, we are using cold gas thrusters, but what you need to have is a finely controllable thruster best proportional thruster, and your usual hydrazine stuff is neither. So hydrazine, you fire and you stop the firing, and then you look what you've actually done, right? And then you fire the next time a bit different, but you can't have that in a mission like that, where it is so critical to control the spacecraft. And the interferometric position measurement, this is a little bit of, I don't think that anybody really doubted it, that we can measure positions with an interferometer. They might have doubted that we can do it to picometers. Actually, just before the launch, somebody told me that, you shouldn't bank on that. In our mission, we tried that as well. We tried nanometers and we never made that. Well, we don't do nanometers either, so never mind. So at the end, Pathfinder was way, way more than that. But let's start with what we did in Pathfinder. So I remind you this funny sort of childish cartoon I had about the free fall, the pushing and the pushing back, which we don't do here. So the test mass and the electrode housing. This is a slide you saw before. Again, a little bit of a reminder here. We used this 2 kilogram test mass, and to do the measurement with respect to the spacecraft, we put that cube into what we call the electrode housing. And you see here one of the sides of the electrode housing taken off and resting on a hand of our trusted scientists. And you see those 2 electrodes here, shiny gold-covered electrodes. And the geometry of the electrodes is such that you can push by activating them in common mode, and if you activate them in differential mode, then you can rotate your test mass. And you can do that at all 6 degrees of freedom, right? You can push in X, Y, and Z, and you can rotate in theta, eta, phi. Everything here is gold-coated, and that has to do with the particular electrical properties of gold, which prevent electrostatic effects. The gap between this test mass and the electrodes here is about 4 millimeters in X and Y. And X and Y is in the plane of the measurement, and Z is across to or vertical to that one. So it's 2 millimeters, so it's a relatively narrow fit. Still, as far as electrostatic drives go, it's an enormous gap. If you have experience with capacitive drives or capacitive readouts, you're typically talking about micrometers there. So millimeters are relatively large, and it limits the amount of control force we can exert on that test mass. I mean, you have to imagine that in LISA Pathfinder, we have also 2 of these test masses, and the satellite is following one of the test mass, which means that we need to gently nudge the other test mass a bit. Plus the satellite is rotating to keep communication with Earth about 1 degree per day, so 1 rotation per year, effectively. And we need to rotate the test masses ever so slightly as well. So we need to exert some forces. The forces are not very large, so the way we do that, we put AC voltage on the capacitors, and if you can either go through your typical capacitor theory and you realize that you can exert forces. Another way of looking at that is to say you shovel more or less energy into the different capacitors, and the test mass will try to balance those energies by rotating or shifting. So typical forces we can exert there is up to 5,000 piconewton. There it is, pico again, right, our favorite unit. In normal operations, we are down to 50 piconewton. This is why I'm saying you roughly see impacts of nanogram particles on the spacecraft, which, if they hit with about 10 kilometers per second on a 500 kilogram spacecraft, they sort of transfer momentum, which you have to compensate with this about 50 piconewton or something like that. the reason why we want to go down that much is that the force noise which we apply as well. I mean, you cannot just apply a force. The force comes from a AC voltage, and the voltage comes from a voltage generator, and the voltage generator refers itself to a voltage standard that you have on board. And in all, you know, in this whole chain, you have noise sources, and this noise that you apply under the force noise that then eventually acts on the test mass, that scales with the maximum of the applied forces. Not with the applied forces, but with the maximum of the applied forces, summed over all electrodes. And yes, for design reasons, you always start out on doing things as simple as possible. So the idea is, we use the same electrodes for linear displacement and for rotation. That might have been a bad idea. Well, not a bad idea, but made things more complicated, because then all of a sudden you realize that it's very difficult to do one thing in isolation, right? Because to do a pure push, you always have to sort of make sure that you apply the same voltage to both electrodes, which you think is trivial, but if you come to millivolt levels, then things become less trivial. So, and here's this slide that I want to spend some time on, which is one our PI considers the sort of the conspiracy against free fall. So, or in other words, whatever can go wrong in free fall will go wrong. And there's a tiny list, or it's actually a large list, but it's a tiny fraction of the total list of the forces that are non-gravitational that act on your spacecraft and that you have to keep in mind and you have to do something against. So one thing is quite obvious, you collide with gas molecules, right? Now, piconewton is not a lot. Yes, gas molecules are tiny, and test masses are heavy. Still, 50 piconewton is not a lot. So you see the collision with gas molecules. Actually, it's one of our dominating noise sources at the moment. And you start wondering, well, I'm in a vacuum, right? I'm in outer space. Well, that's true, but you're not in interplanetary space. You're inside a spacecraft, where the vacuum is less than ideal. So the idea was to have this whole test mass ensemble, and I'll show you that later, in a vacuum system, and then evacuate that vacuum system down to free space with a tube that opens up to the bottom side of the spacecraft, and you just open a valve. That works okay until you realize that these gaps here are 4 millimeters, and there's a complicated geometry of that tube that goes out over there, right? So the poor gas molecule that has to find its way, remember, you cannot suck, right? All it does is that it goes along and eventually gets lost in free space. It takes a while for the gas molecules to come out there. Plus, if you have a temperature gradient, then this gas up here is a little bit hotter than the gas down there, so it carries more momentum, and you want to avoid temperature gradients as well. Electrical fields and surface potential, this is why we take it over. So you've all learned in undergraduate classes that metals are conductors, and therefore they form an equipotential surface. Well, that's a lie. Right? Yes, they are conductors, but only up to a certain level. If you look to the millivolt level, you realize that they have some sort of funny shaped areas that correspond with the underlying crystal structure of the metal, and where the difference between this one and this one, or this one and this one, can be millivolts. Now, why is that a problem? Because when you apply a constant voltage to the outside, which is the electrode, your capacitor reacts in a way, and it reacts differently depending on the potential of this test mass at that given point. So even if you think you're applying a pure push, something different will happen. Now, none of that would be critical if those areas would be static. They're not. They change over time. Of course they do, right? Why wouldn't they? And they certainly change on timescales of millihertz, 1,000 seconds. So the way to reduce the effect here is to use a friendly metal, that where those differences are as small as possible, which is gold. It's also a shiny metal, so it helps. But the other trick is to make these gaps as large as possible so that effectively the electrodes here see this test mass from a large distance, and vice versa. So this is why we go for relatively large gaps, and this is why you have to go to relatively large voltages to exert something horrendous like 5,000 piconewton. Charging by cosmic radiation. I think we had that question before. Let's come in with the next picture. I have that here. This is a GN4 simulation with a solid model of the spacecraft. And you have protons, high energy protons coming from everywhere, from the sun and God knows where. And they hit the spacecraft and they just go right through. They impact relatively little momentum because most of them go right through, but they certainly leave enormous amount of electrons in their wake. So wherever they hit, things are negatively charged at the end. And you have to get rid of that charge somehow, because otherwise the static forces you have to apply are getting larger and larger and larger. And remember, the static forces, the larger they become, the larger the noise in the static forces become. So, your noise grows and grows and grows and grows while the test mass is charging up. So the way we take care of that is we illuminate the test mass with a UV light. And this UV light knocks out electrons from both the test mass and the electrodes, and depending on how we bias the electrodes, the electrons go one way or the other and vanish. So we can equalize the potential, also known as grounding the test mass. Now, grounding is a lot of a strange concept on the satellite, but we just say we equalize the potential there. The gravity gradient inside the satellite I already told you about. You need to be extremely careful in doing that. One of the biggest sources of the gravitational gradient is actually the other test mass. So the way you cope with that is you put another compensating mass directly behind you, and because the other test mass is about 38 centimeters away, and the compensating mass is maybe 2-3 centimeters behind your back, you can actually flatten out the potential relatively well until you forget about that you have to do that, and then you go into last minute panic, never mind, which we actually did. So people did forget the other spacecraft, the other test mass. Unfortunately, it was still time to redesign the compensation masses. It tells you what can go wrong will go wrong. Radiation pressure of the laser, as I said, I read out, and you will see some interesting designs as well for the optical bench. We read out this position of the test mass not only capacitively but also with the laser, because we have it on board, why not? And when the laser hits that test mass here face on, it exerts a force, again this 2p/c force, and if the power P changes, so does the force. So you need to make sure that your radiation pressure noise is small enough in the region. So magnetic fields, internal, external, I already told you about magnetic fields, that they are not exactly our friends there. We try to compensate that by having a low susceptibility on the test mass. Obviously 0 you never get, so you make it as small as possible. And we were very worried about permanent magnets, so we had a very strict ban on ferromagnetic materials around the test mass. A bit further away we allowed them because we had to. The laser needs a magnetic field to operate properly. But fortunately, magnetic field cleanliness protocol is well established with spacecraft engineers because of missions to the magnetosphere and all that. So there they know what they're doing. Still, there's a little bit, magnetic fields are always a little bit iffy. So, and many other sources that are too numerous to mention. But here's a little problem. I had the question earlier from up there about how do we hold the test mass. Well, there you go. Here, this is the test mass. This is the dummy test mass. This is the so-called caging mechanism. And you see up there and down there, you see little pins coming up, and you see that here it's rotated horizontally, and you see them here and there. And they grab the test mass like that. Right? Now remember, the test mass is 2 kilograms. The launch manual of your launcher, the Vega, says that you have to withstand a quasi-static load of 70 G. Now, the launcher will never exert 70 G, right? But the problem is during launch you get a huge amount of noise from the engine, and while Vega is still close to the ground, that noise feeds back to the structure and rattles the structure. Well, this is the biggest sort of acceleration noise and acceleration load you will have during launch. And if you want to have compensate 70 G, 2 kilograms, with the required safety factors, you have to pre-clamp with 2000 Newton. Okay, 200 kilograms, right? So the two fingers pressed with 200 kilograms on such a wonderful material that's called platinum, which is not known to be exactly very strong. So what will happen then, eventually you say, okay, let's release that, right? So you unload and you pull back. By that point, you get cold welding. Right, because everything is in vacuum, everything is ultra clear. So you have the problem that your test mass sticks to one of those fingers, and you need to get rid of that. You need to be able to retract the plunger there and make sure that the test mass is free floating. Now, pushing is easy, pulling isn't. So what do? Well, we design a system that pushes. So effectively, this is a ballpoint pen. Right, where you unload the 2000 Newton pre-force on that green one here, and then you activate the ballpoint, which has only a few Newton, to break the adhesion here, and then adhesion is broken, and because this had 2000 Newton and this only has a few Newton, then you can hopefully retract that one without too much adhesion, and then go away. Did that work? Yep, sort of. So the idea, to give you an idea what we required to do. Remember, the gaps are 4 millimeters and 2 millimeters. We can only exert 5,000 piconewton. Only. That's quite a lot. So you want to release the test mass with a velocity that is small enough so that during the time it drifts over to the wall, the test mass, the electrostatic forces have time enough to capture. Turns out it's micrometers per second. Slow, right? Now, okay, that didn't work. So it turned out when we released the test mass that this preload, the remaining preload here, was large enough to effectively, as our PI said, you build the most effective catapult with the tools you had available. So elastic deformation and everything here, and the release of the elastic energy led to a velocity of hundreds of micrometers per second. So what effectively then happened is that the test mass drifted against the wall and bounced a couple of times. So this is why it rattled, but it really didn't rattle. I mean, it moved very slowly, and it pop, 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 and then the energy was gone. And then we could capture it with an electrostatic, and then bring it back to the nominal position. So this is one of those things, and this mechanism here single-handedly was responsible for quite a number of delays, because again, what can go wrong will go wrong, and there were worries about the 2000 Newton actually destroying the test mass by driving through or splitting it or whatever. And then the release mechanism didn't work in the first go, and didn't work in the second go around either, so that had to be redesigned. And then this whole thing has to fit in a vacuum system, which isn't trivial either. And so that is one of those things that caused us quite a lot of headache. But this is why I'm saying it's just an engineering problem, right? This is not physics. This is only engineering. Which I said, if you hear that term, head for the horizon, because these things that are considered to be easy and simple typically are not. They are only simple and seem to be easy because you haven't thought about them enough, because you're not experienced in that field. Right? You probably think a lot about the things that you know are difficult and therefore have a good feeling how difficult they are. These things that say, why don't we do it like that? Well, right, because they are difficult as well, if you only knew what we were talking about. So another critical thing for the free fall is this thruster over there, right? So this one. And as I said, what we want to have is something which is reliable, gives us a thrust that is known, and in the business we are talking about thruster dispersion, which means you command 1 Newton, the thruster said, come on, I fire something and you tell me what it was at the end, right? And that's okay for pretty much all missions, because what people do is a sequence of burn. They start with a relatively large one where they say, I need 100 Newton. They command your engine and say, give me 100 Newton. The engine fires, eventually it stops. Flight dynamics looks at the situation and said, oh boy, that was 110 Newton, right? So the next step is not 50 Newton, but just 40 Newton. And by the fact that we know that this thruster overfires, maybe we command 35 Newton. And you iterate yourself to the right solution. If you have enough time, you can do that. If you have to do that in a closed loop system, where the system has to react to external disturbances to your spacecraft, this is a hopeless situation, right? Because you introduce too many delays. So you want to have something which is reliable, gives you the right amount of thrust every time, a predictable amount of thrust, at least after you calibrated it. It should be finely enough controllable. So you don't want to have firing either 0 or 100 micronewton, right? Or you want to do that within a micronewton or something like that. It should be reasonably fast, so you need to command it within, 10 hertz or something like that. And eventually, after many failed attempts to make electrospray thrusters work, which is effectively something that spits out ions, we settled on a technology that Gaia is using as well. They're cold gas, so liquid nitrogen-based thrusters, not liquid, just nitrogen-based thrusters, cold gas, in contrast to the hot gas that comes out of a thruster which uses chemical energy, like hydrogen. So the maximum design thrust was 500 micronewton for these thrusters. We operated them typically with about 30 micronewton. Now, how much is 500 micronewton? You need 100 thrusters of those to lift a sheet of A4 paper. So it has almost no thrust at all, right? Still, that's enough to control the spacecraft to fly around the test mass. Most of the thrust we use is used to counteract solar radiation pressure. So the spacecraft stares at the sun with the solar panel because it needs energy. So it exposes about, 4.5 square meters or so of solar array to the sun. So it receives a certain amount of radiation pressure, and the thrusters on the backside have to fire permanently to keep that in check. And if the solar emission varies, which it does, on timescales of about 5 minutes, which is something like about 3 to 4 millihertz, which is roughly where we want to measure, so that's a bit annoying. You have to vary the thrust of the system. And finally, we use about 100 grams per week, give or take. Half of that roughly for the for routine operation, and the other half for something that our flight dynamics people call station keeping. The orbit, LISA Pathfinder, it is not stable in contrast to the LISA orbit, which means if you don't do something, it drops out of that orbit, so you need to, every 2 weeks, nudge it. We nudge with the same thrusters where you need 100 of those to lift an A4 sheet of paper against gravity, right? So that's a very gentle nudge. And you typically nudge for around 10 hours. when you're done nudging, then the spacecraft is fine for the next 2 weeks or so. So sloshing was a question. As I said, we don't slosh because gas doesn't, but here's an interesting thing. So this is the gravitational impact of our gold gas. That's cool. No, it's cold gas. What we see here, this graph caused endless confusion with the referees, because they insisted that we labeled it the wrong way around, but we didn't. So this is what we see here is the measured differential gravity between two test masses. So effectively the force between the test masses. And you see it drops down and it goes to 0 around here. So this was, as expected. And then we said, well, let's try something. Let's correct that for the propellant gravity. So let's take out the effect of us using cold gas and depleting the reservoir. And then it turns out the curve is much smoother and much nicer. And the reason for that is that the fuel is not isotropically or smoothly distributed around the spacecraft, but you have tanks, right? And you use that tank for a while, then you use that tank for a while, and then you use that 2 tanks for a while. And they go back, right? And you do that in such a way, because you're clever, or you think you're clever anyway, that around a certain time, the gravity planned is around 0 here. But this is because the rest of the spacecraft and the remaining fuel conspires to compensate here. So this is the curve that would have really been there. And now you ask, why is it going down? And this is a very interesting question to which I have no good answer. But this is what we wanted, where we wanted to be, where we thought is our best measurement. And if you see, which is how I said, the guys in mission ops tell us you used 100 grams of gas, and if you see these are 10 days, so these are 2 weeks, we can see the decay in self-gravity of the spacecraft. So turns out that we can measure the amount of used gas better than the flow sensors can. Now, it's a pretty impressive performance for a spacecraft, but it's a pretty expensive flow sensor as well. So if you pay 400 million to do that. But again, this is the effect of the gravity of a few hundred grams of gas. So here's a sketch of the, remember I thought complexity is your enemy, and we can't have the full LIGO layout and all that, and we make it much more simple, and we end up with something like that, which is really much more simple. It isn't, right? You need a certain amount of light path on an optical bench to do a proper interferometry. You want to measure the distance between these two guys. You want to have a reference interferometer just because that's cool to have. You want to have an interferometer that you use to assess the frequency fluctuation, so you make it unequal arm on purpose, so that a white light interferometer with equal arm lengths is insensitive to frequency fluctuations. So if you want to measure them, you make it as unequal as you can. And then there is an interferometer that measures this test mass against this test mass, and an interferometer that measures this test mass against the optical bench. And this one is the one that is ultra sensitive, and this one isn't. And the reason for that is obvious. This one against this one effectively cancels the effect of the optical bench. So the optical bench can jitter around, and we don't see it very much, whereas where you measure the test mass against the optical bench sees the full movement of the optical bench. And the difference is striking, so we are talking hundreds of picometers against femtometers. So here's our cool 3D sketches. So this is the one that measures the red one. Purple here measures the distance between the test masses. And there we have the reference interferometer. Despite the fact that the arms look unequal on this optical bench, they are not, because the path length difference occurs somewhere upstream and has to be taken out on the optical bench. This one, despite the fact that it looks as it had equal arms, is not. So this is the frequency reference interferometer. Endless source of confusion. And here we have the thing that measures only that against the optical bench. Now, these slides are stolen from the group in Hanover, who played a significant, if not dominating, role in the design of that interferometry. How do you build such an optical bench? The slide is stolen from the University of Glasgow, from Dave Robertson. The technology is stolen from GPB, which is this hydrocatalysis bonding that LIGO is using as well to attaching the ES to the test masses. So we use the same technology, not exactly because it's needed, but because we know how to do it. And there's very often compromise in space technology where you say, well, yeah, but we know how to do that, right? I mean, no need to investigate maybe some glue with a UV curing process that works as well and only costs 80%, and once you did all the development 3 times as much, there you go with what you have. And the interesting thing is that these things cannot be adjusted at all, so they are put on place, they are bonded, and they stay there. So if you make a mistake, you have a bad afternoon, so you better do not make mistakes. So the Glaswegian group spent a lot of time to developing procedures and protocols to make sure that they don't make mistakes. And one thing they managed to do is the repeatability of the positioning. So you put that thing down, you measure the contrast of the interferometer, you take it out without bonding, you put it down again, you measure is about 10 nanometers. You arrive at the position where you want to be to within a few microns, which is pretty much the limit of current technology in positioning machines. So the critical components, you want to make sure that the light hits the test masses when it comes off the optical bench. You want to make sure that it overlaps at the recombining beam splitter, because otherwise you don't see interference. And you want to make sure that those path lengths that need to be the same length are the same length. And here's a boring slide, because I couldn't fit it on the previous one, which just tells you how well people did, the Glasgow group. So the flight model where -6 micrometers and -15 minus in Y and Z out for one test mass and the other test mass. On the flight spare, which is an identical optical bench, just in case the first one breaks, numbers are comparable, and everything was within spec to within 25 micrometer. So you know how to measure distances and change the distances with the interferometer, but you need to measure angular alignment as well, statically for the optical bench during build, and later in LISA for keeping track of the movement of the satellites. And here's an interesting technique which is clearly undersampled here on that slide, but I'll have to explain that a bit better. We call that differential wavefront sensing. Effectively, you have 2 interfering wavefronts there, the red one and the blue one, on a split photodiode. And if you tilt let's say the blue wavefront down, then the phase lags on that one and advances on that one. And if you take the difference of the signal, of the beat signal, you see, can immediately read out the tilt of the wavefront, and you can zero it if you want, or you can just measure it and write it down and keep a log of that and telemeter it down eventually. There's a relatively large amplification ratio of between the angle of the wavefront and the angle and the phase difference of the beat, because the different frequencies in the audio range and the light frequency. You don't need a reference, because you effectively define where you want to be with your split photodiode. And I stole that slide from Gerhard Heinze from Hanover. I like that statement. It's immune to several noise sources. Yeah, it is. it's a reasonably good measurement. Again, you can't read that here because the resolution is crap, but the black one you can see, that was the requirement. Ignore that one because at high frequency everything is easy. At low frequency you don't have to be, and you see here in places the cyan and the purple one are above the requirement, that's bad. The other ones are below. That refers to different stages of the testing in different vacuum systems. And one thing we learned in LISA Pathfinder is that we tested things on ground very extensively in very elaborate facilities, but if you go down to millihertz, really ground-based facilities are cutting it. You have noise sources that are exclusively driven by your facility, like air conditioning in the surrounding room, or people coming and leaving from work. Low frequencies are not fun. So it turns out that pretty much all our performance in flight is significantly better because we are far away from any noise sources. So we use this differential wavefront sensing to align the interferometer actively. You saw the light passes over the test masses, so if you rotate the test mass, you can unshift the test mass, you can align the interferometer. And this is what happened. This is in-flight data. So we had the X12 interferometer is the interferometer that goes via both test masses. The X1 is only the one that reads out X1. And we starting out, coming out of the release of the test masses, so effectively from the cold, we started out with 7% and 3%. So when we aligned test mass 1, the whole thing went up to 99% on X1. It also went a little bit up in the other interferometer, but clearly not to 99% because test mass 2 was still not very well aligned. And then at some point we switched on the control loop for the attitude of test mass 2 to say line test mass 2, rotated to best contrast position, and it went up to 99%. Now, in ground testing, never more than 93% was achieved with movable mirrors instead of test masses. And I still remember Gerhard sitting at the control room saying, "Oh God, please don't go beyond 1." Right? But it didn't, so that measurement is okay. And it stayed there till the end of the mission at 99%, so it never changed. So this is a good example how things in space can be much easier because there's nobody around to annoy you or a measurement. So this is a graph which shows you the performance we have in displacement measurement. So this is not the acceleration measurement. This is just the performance of the interferometer. And sort of the consolidated best number is 32 femtometers per root hertz. I told you when the colleague told me, nanometer is difficult, don't count on that. I said, well, we don't know nanometers, we don't even do picometers, we do femtometers. That is shock noise limitation, essentially shock noise from the laser we use, or at least laser noise. I wouldn't put my hand onto the fire for shock noise, but this is mostly laser noise driven. The structure doesn't change much. I wouldn't say at all. There are some unexplained effects which we don't 100% understand yet, but it's essentially unchanged from the ground measurement, which sort of validates your mounting technology, right? So you use hydroxide catalysis bonding, which was developed for space and large temperature fluctuations, and it works, surprise, surprise. So, and just to tell you things that are difficult, sometimes if you do low frequency measurement, each data point here is 6 hours. So it takes some data taking for low frequency. So 3rd of December 2015, that's interesting. We launched that thing, and Don't think there's much to hear.
10, 9, 8,
We're launching from Kourou.
6,
Countdown is in French, obviously.
4, 3,
Why would they use English?
1, top.
Come on.
Allumage et décollage de VV06.
And off she goes. And there she vanishes. Because clouds. So even the equator doesn't always have nice weather. If you remember, if you have seen shuttle launches or other launches of the Soyuz, which brings astronauts to the ISS, you have a feeling that this thing goes off extremely fast, and it does. Solid state boosters, solid fuel boosters, which are effectively controlled bombs, pack an enormous amount of punch, and this thing is a very, very small launcher. Right, so it brings it up extremely quickly. Now, fortunately, our graphics department anticipated the fact that there might be clouds, so the rest is now animated. We didn't have a camera on board. It was a low-cost mission, we don't do that. We don't have a satellite that flies next to it. There goes the fairing, wobble, 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 off she is. There's separation from the propulsion module. At that point, Pathfinder is on its own thruster. That was the engine of the second stage. This is still the Pathfinder propulsion module you're seeing. So you see the rather interesting orbit. So we go a couple of times into what we call orbit raising maneuvers, or in the terms of MOC or Mission Operations Center hair raising maneuvers, because they didn't like that, because there's a certain risk involved, and there it drifts out to the nominal orbit, which looks a bit like a potato chip around L1, the liberation point around Sun and Earth, and there you go. And this orbit is about 180 days once around. And this is why you see that you have to rotate the antenna on the spacecraft is fixed, so you can't rotate the antenna. So if you want to communicate to Earth, if you're there, you have to rotate the antenna to a different point from there. So this is why the spacecraft rotates with about, I said, once per year, twice per year, but with a variable rate between 0 around here and maximum around there, or vice versa. So there's that. This is sort of the nice animation how to get there. As I said, these hair-raising maneuvers here, that's the price you pay if you have a launcher that is relatively cheap and weak, and where you almost exceed, I mean, you're right next to the performance limit of that thing. So you can't pack a better engine or use more fuel to go straight to that orbit. You have to sort of nudge yourself up a bit and a bit and a bit and a bit. So, and with the next, I have another movie here which shows you a little bit better, maybe a little bit better than what we're actually doing. And I always fail to stop that thing without translating to the next slide. So I try to talk quickly here. And we'll see if that works or not. So these are our two test masses. You know, instead of 2.5 millikilometers, 40 centimeters apart. Optical bench, as I showed you before, there's the boink boink, the interferometer that measures test masses. So we pack them into the electrode housings, into vacuum system. Now you see if the whole thing moves up and down, the test masses stay where they are. The pink stuff there is UV light, by the way. So then we put on the side slabs to do the structural integrity of the whole thing. We pack it into the central cylinder with thermal insulation. Then the spacecraft comes around, then the lid comes on the spacecraft, which is the solar array. So yeah, you see the cold gas thing is firing, and then Christophe, our graphic artist, decided to put some sort of rain into space, which is of course not rain, but this sort of symbolizes the solar illumination that comes in. And here the cold gas thrusters, these things with on average 50 micronewton fires, and you see they are angled. There are 4 of them here, and there's a third cluster on the backside which you can't see. There's American hardware on board, which is the colloidal thrusters, which are a bit different from the cold gas. They use an ionized liquid, a little bit like an inkjet printer. So we tested them as well. they worked very well as well. Unfortunately, one of them developed some sort of a hiccup. These here are plain old radiators. So radiators in space are white, not black. You can ponder about that, why that is. Let's just say black would not have the right effect. Sun seekers, so things that stare into the sun and give out an alarm when we are pointing away from the sun, because if you're pointing away from the sun, then you lose electrical energy, which you might need to steer back into the sun. So if the satellite drifts out within 10 degrees of alignment with the sun, all hell breaks loose and the satellite goes into survival mode, switches off your experiment, and turns into the sun and waits for ground control to establish happiness again. So, what do we achieve? What did we achieve? A crappy resolution graph. So, frequency 10 to the minus 4 hertz to 100 hertz here. This is the original LISA Pathfinder requirement. We deliberately set that a factor 10 higher than we thought we need for LISA in performance, and we restricted it down to a millihertz, not to 10 to the minus 4 hertz. And the reason for that one is that testing becomes exponentially expensive if you go down here. And after all, this is the Pathfinder mission. You don't want to spend all the money on that one, right? So this is the original LISA requirement, and this is an acceleration, by the way. This is now our PI's favorite unit, meters per second squared. So the red line is pretty much, well, there's a gray line here. This one, which you can't see here because it's the same as the red line, but then it's going up there, is pretty much what we had at day one. So we could have stopped there. We met the LISA requirement almost. You see the LISA requirement is a little bit lower here, but we are way below the Pathfinder requirement on the interferometric side. Here at high frequencies, we are ridiculously far below the requirement, but don't be fooled. This is due to the fact that the LISA requirement here is based on a few hundred picowatt received laser and not on 10 milliwatts. So this gap simply represents the difference in shock noise. This is a published data, which is why I can show that we are, at the moment, we are better than that. We are below the LISA requirement by quite a bit. The reason for that one is that this area here, where the flatness is effectively dominated by the gas pressure. You know, the air molecules that hit your test mass from all sides and rattle the test mass around, there are fewer of those, so the Brownian noise goes down. Also, we tried some temperature experiments where we lowered the temperature of the satellite, predicting that then the noise should go down, which it did. Now, an interesting thing is over here, which you can't read. It says centrifugal. So I told you that the satellite has to rotate by about a degree or so per day, right? So the test mass don't want to do that, but they have to. They have no choice because we push them along. Well, it's orthogonal to the direction of the measurement, so that shouldn't matter much. It doesn't. Well, it does a bit, but the crucial thing is to push them along. You need to have a certain amount of force in the y direction. And I told you that the noise is proportional to the total amount of force that you exert on the test mass. So this is the noise due to the fact that the spacecraft rotates with 1 degree per day. Right? This is not the centrifugal force, that is the noise on the centrifugal force. And if you do some magic, by simply reading out the spacecraft rotation independently through the star trackers and calculate the rotation rate and take out that noise, you end up here, 10 to the minus 14. This is the famous 10 femtonewton, the famous 10 femtog per root hertz, about 6 orders of magnitude better than has been ever demonstrated in space or everywhere for that matter. Other things to note, here are a couple of features which we have no idea about. quite true. I think this is 10 to the minus 1, 10 to the 4, 3, 2, minus 1. So somewhere around here is a line that comes in through the cold gas thrusters. We have no really idea. We just know they are cold gas, that it comes from the cold gas thrusters, because if we switch to the American system, they're gone. We still don't know where they're coming from. And experimentally, we will never have an idea, because we switched off LISA Pathfinder for good on the 18th of July this year, so just a couple of weeks ago. Again, I said at the beginning, why LISA Pathfinder? At the end, LISA Pathfinder was much more. This is a little bit my take on what LISA Pathfinder was much more about. Was a great physics experiment. It was supposed to be a technology demonstrator. It turns out to contain an enormous amount of interesting physics, things you never thought about. For many things you hope you will never hear about again in your life, but you have to deal with that. Like this centrifugal correction, where at some point you think, really? But okay, if somebody demonstrates to you that if you take out the rotation rate, everything is good, because okay, probably was centrifugal forces. This is something which will not mean much to those of you who have never been in the situation to talk to spacecraft engineers, but typically there's a strict separation between spacecraft and payload. Right? It's like a telescope, the separation between a mirror and a focal plane instrument. Or people usually say, well, we do this, you do that, we prepare everything so that you get the right pictures, or you do that. And that doesn't work in a mission like LISA Pathfinder. Gravitational balance is an issue, right? If somebody decides to use feed branch 1, which drains that fuel tank over there, you better know about that. Even better, he should better ask you about that, if this is actually the best thing, or shouldn't we switch to that one which drains those two tanks, which keeps the gravitational balance better for long. Many things like that. Temperature, some routine things that people do during station keeping. Oh, we always do that. And then you realize that we always do that reads out a star tracker where all of a sudden 20 milliamps are flowing that you haven't accounted for, and you see the magnetic effect and you see the thermal effect. So it's different from normal payload and spacecraft separation. It's really a tight integration. For those of you who work on LIGO, that will come to as no surprise. It has been extremely good learning tool for all involved. That means industry, as I said, when we started, you got, for most of the things, you had the industry telling you, oh my God, that will never work, or, which is even worse, don't you worry, that will, we know how to do that. And they're wondering, how do they know, right? They never did something like that. And this sort of clueless optimism is much better than it's much worse than clueful pessimism, in my experience. Because at least with the pessimists, you can get them talking about their problems and not just denying everything. Management as well. There are things where you realize that a sort of ragtag group of engineers and scientists behave differently than a streamlined company. Not worse, not better, just differently. It was a very enjoyable experience, I think, for most of us. Stressful, yes, but very enjoyable. It's great to have data. And the best thing for me, obviously, and for the gravitational wave community, is we had a convincing demonstration of the LISA technologies. And to be perfectly honest, I think not everybody expected that. I think there were a lot of people who sort of had the back on their mind, it might fail. Okay, we had that all the back of our minds, but certainly nobody of us expected to do that well. But sometimes you can be positively surprised. As I said, on the 18th of July, we had that one. So this is a movie from the inside of the main control room in Darmstadt. You see the mission, the operations manager, Damien Texier from ESA, I think neither Stefano nor Carsten are somewhere in there. But what you see up there is the signal returning from ESA Pathfinder carrier and sidebands. So this is the communication signal from Pathfinder, and you hear people talking. At some point I need to dewobble that. And there she goes. That was the end of the mission. We switched off Pathfinder by uploading a new operating system that was effectively just a list of names of all people involved in the mission, and then sent the reset command. And then the computer goes into reboot mode, loads up a corrupted memory, and that's it. Right? So the spacecraft now will, for the next 100 and plus years, not come back to Earth. The worry was that it will, so we needed to deorbit it first and to put another orbit, because the worry was that those wonderful test masses will survive re-entry and kill somebody, and so now it will not come back within a time frame of 100 years, and most likely eventually will drop into the sun. So who knows? Okay, thank you. If there are questions, we still have a little bit of time before Joan is up. Okay? Yes?
In place of the cold gas thrusters, could you not use some kind of electrostatic propulsion system or anything like that?
Yeah, if it works. So this is a little bit a sad story. So we planned from the very beginning to use a thruster that's based on cesium, liquid cesium, ionized through a high voltage, pulled up into a Taylor cone, spitting out little ions at the top of the cone, and then being blasted out. This is one of those things that sound wonderful and brilliant until you try it. And it was never possible to make it work. Part of that has to do that it is an absolute and completely idiotic idea to use a material that you can't test, right? If you expose cesium to atmospheric pressure, all hell breaks loose. So you can only test it in vacuum, which makes your testing cycle really, really annoying. You open up the vacuum system, and the first thing you do is to grab your fire extinguisher, because that thing coated the inside of the vacuum system with cesium. You open it up, and the humidity in the air has a fun couple of seconds with the cesium. And we had hoped it will work. Frankly, at that point, it was even our only option, because the cold gas thrusters weren't developed. The cold gas thrusters we had till then had an off at about 30 micronewton. So this one has an off at about 1 micronewton, which means you can command 0 or 1 and above. And if you can command 0 or 30 and above, that's a problem, right? Actually, it wouldn't be a problem if you can command it much more quickly. If you could command it with a kilohertz, that would be okay, but then it's gas, so you really can't, because you're limited by the speed of sound in that system. So electrospray thrusters would be cool to have just for the technology, and they sound really cool and all that. The sad story is they don't really work. Now JPL, who builds the colloidal thrusters, they work. They have, however, at the moment, still a lifetime problem, as we've seen in Pathfinder, where they had a couple of failure modes that are not fully understood. For the cold gas, we are lucky enough that Gaia does the long-time testing for us. I mean, as long as Gaia is up, they're using their cold gas thrusters, which are the same that we use. So it's one of those compromises. You say, you sacrifice the cooler technology for one that actually works. But it's tempting, I tell you, because it's so much less mass and so much cooler, but what can you do?
Could you
expand a bit on how LISA would measure the spacecraft to spacecraft distance, how the phase locking of the laser works, and how you measure the phase?
So what I haven't told you is how the measurement actually works. I told you it's separated into 3 parts. So in principle it's enough that you measure the phase of the incoming signal with respect to one local oscillator, and then you measure that on the other arm as well, and then you measure the 2 local oscillators against each other, and then you have your measurement chain established. Now, and you do that in each direction, right? You receive that light and measure, and you send out, and the other guy measures. Now, it turns out if you as well make sure that the outgoing light is the phase of the outgoing light is an exact copy of the incoming light, which is what phase locking means. I mean, you just build some electronics that makes sure that there is a fixed phase offset between the 2 lasers. Then because you drive one of the phase differences to 0, because of the one that you would normally measure, you drive that to 0, so you don't have to transmit it to ground, you save some data, right? So, but in principle, you don't need the phase locking. Practical considerations tell you that you better have it because it brings your data rate down, which data rate is an issue. So you would receive the light, your 100 picowatts, you will beat it with a local oscillator, and then you look at that beat node, and you take some light from the outgoing laser and beat it with the same local oscillator, and you see a beat node, and you compare those 2, and you adjust the frequency of the one laser until the 2 are the same. This is a standard phase locking technique. So we can do that, we don't have to do that. The second part of your question was, again, was phase locking and?
How phase locking works.
Or how phase locking works, exactly. Well, okay, beyond what I just said, you have to make sure that you can control the frequency, because phase is just the integral of the frequency. You can just adjust the frequency, and the phase will do whatever the phase does, right? And so you just have to make sure that you can control the frequency of the outgoing laser fast enough. Now, what is fast enough depends on how quickly the phase of the incoming laser changes, and if you keep that within reasonable technical requirements, it turns out that those lasers that we use can be controlled on the scale of maybe a number of microseconds, and that's good enough. Right? It depends a bit on exactly the noise that's on there, but if you can control the laser within 10 microseconds, so effectively if you can shift the phase by 2 pi within 10 microseconds, you are fine. Then your control system will take care of that. Okay. Any more questions? All right, everybody's tired. Good.